Yep. So this is graph theory session. I am Sidhant, and that's pretty much it. So let's start off. And in case you have any doubts, like in between or anything, either you can unmute yourself, or sometimes people are shy, so you can even write on the chat. And like prefer to make all your messages for everyone so that other people can also see your doubt and like they know what doubt I'm talking about. All right. Um, so I'll start sharing my screen. And I think you guys can see the chat window. I hope you guys can see it. All right. So the agenda for today is firstly, we'll give me a moment to remove this. Yeah. Binary lifting to calculate. So I looked at the votes for the poll that we conducted before, and I mean, I'm still confused about whether we should cover BFS or Dijkstra. But for the first topic, I'm quite confident that we should cover this, which is how do you calculate the lowest common ancestor in a tree for two nodes fast, that is in log n. So there is a slow method which we'll like quickly go through or something, but like the slow method is kind of like order n-ish. This method is, so we'll first cover the idea sketch on pen and paper, and then like you can just see the agenda. Then we'll explain how to do path aggregates using that lowest common ancestor thing. So in path aggregates, what I mean is a question something of the sort, given q, which is big, like around 10 to the power 5 queries of the format u comma v, find the max value in the path from u to v. Path here means simple path. I'll explain simple path later a bit, but like the idea of simple path is that in a tree you can't like go back. That's the simplest route possible from u to v. You can't just like keep on traversing a node multiple times. That's not allowed in a simple path. So then we'll do a code demo of the normal binary lifting technique along with this path aggregation, which so as a motivation to solve, like to do this technique, we can solve Enoch 1. And I think I have the problem somewhere here. Yeah, Enoch 1. Enoch 1 has a relatively much simpler solution also. So it's not like that this solution is the only solution. The easier solution exploits prefix sums idea. We won't go through that solution. Finally, we'll try to show an analogy between a straight line tree with path aggregates with respect to a sparse table. Okay, and for the second topic, I'm not sure how many people are there on the chat, but like we can have a vote here to just see how many people on the Zoom call are familiar with BFS or Dijkstra. I obviously assume more people are familiar with BFS, but I just want to get a voting. So if the vote says like if we get a kind of like a vibe that a lot of people don't know Dijkstra, then we can just cover the BFS thingy. But if we feel that enough people or quite a good number of people know Dijkstra, then we can. Oh, I mean, there is a proper poll. I'll just open it up like in some way. You don't have to put on the chat. Yeah, but if we feel that a lot of people do know BFS already, then we can cover the Dijkstra one, because in the previous voting, technically Dijkstra won, but like I'm not sure like how many people will be familiar. Like the techniques that I want to cover for Dijkstra, I would be assuming that you know the basic Dijkstra. That is like the priority queue or the set or whatever log n-ish one data structure that you use, and you implement just a basic Dijkstra. I'll assume that you know how the basic Dijkstra works, and then we can do variants upon it. Because in competitive, generally, there are very few questions in which a classic Dijkstra is used. So let me see. Okay, we have 36 participants. Okay, let's just start with the first topic first, and then we can, like, once we have enough participants, then we can do the poll for the second topic, which is either BFS or Dijkstra. You don't have to put on the chat. I mean, there is no particular reason because I can't keep track of that. Okay, so can people see the whiteboard? Just like reply on the chat or something. Cool. So the first topic is lowest common ancestor, which people a lot of times say LCA. The idea is, let's say you're given a tree. Okay. I'm assuming everyone knows what a tree is. A tree is basically n nodes, n minus 1 edges, no cycles, and everything connected. Right? If you have all these properties, I mean, technically you just need the first 3 properties, or like whatever, first, second, fourth property. But like, yeah, you obviously need the first and second property. So yeah, let's say you have a tree, and then like, I'll not motivate it right now, but let's say the question asks you to find the lowest common ancestor of 2 nodes. So let's say this is the node U and this is the node B. That means we are trying to find the bottommost guy who is an ancestor of both of them. By ancestor here, I mean he's like, okay, example for you, U's ancestors are this guy, this guy, this guy. These all 3 are U's ancestors because they are above you. But example, this guy is not a U's ancestor because he's not above you in the sense that in his subtree U is not there. All right. So all these 3 red guys are U's ancestor. And then for V, this guy, this guy, this guy, this guy are V's ancestors, right? This is the V and this is the U. Now, what the question asks is basically the lowest common ancestor. So in this case, the lowest common ancestor is this guy. Not this guy, because he's the bottommost one, who is a common guy. Common as in he's an ancestor of both of them, U as well as V. So generally when you define LCA, you define for 2 guys. So LCA of U comma V is a node, which I just defined here, that it's the lowest guy who's an ancestor to both of them, right? So I hope everyone is clear what LCA, the word, means in graph theory and tree general, that you're the lowest guy who's common and an ancestor to both of them. By ancestor here, we mean that you lie in the parentage of that guy. So you can think of it like a family tree also. This is the grandparent, maybe this is his 2 children. These are 3 children of blah, blah, blah. Then ancestor technically means family ancestry. That this guy's family ancestry is these 3 guys. I mean, probably that's how the word originates, right? Any doubts in the very definition of LCA? If yes, then please speak up. Otherwise, we can just move forward. Like, assume that you know what LCA means. Okay, so now the slow solution. So let's say you're given U comma V, and in ON, you'll find the LCA of U comma V, right? So in this case, in this graph, the slow solution is basically, okay, first do a DFS on the tree. Okay, Het Patel asked me to repeat. We just explained the definition of LCA. LCA, like what does LCA stands for? Lowest common ancestor for 2 nodes in a given tree. And the definition is basically more or less that you're given 2 nodes, U and V, who's their lowest common ancestor. It speaks for itself, but like, yeah, the ancestors of U are the nodes in red, the ancestors of V are the nodes in green, and the bottommost guy who is both an ancestor of red and who's both an ancestor of U and V. So it's this guy, right? It's not this guy because he's not the it's not this guy because he's not the bottommost one. Cool. Yeah. So yeah, how do you do it in order n? That's the first question. Okay. Yeah, this was U, this was V. Yeah. So for the order in the slow method, the idea is that you first do, okay, in either method, you first have to do a DFS on the tree and get some information of the tree. And then this slow method is per query ON, right? This is per query ON. That's the slow method. And the fast method is per query log n. So that's what we'll be aiming for. But we'll first go through the slow method so that you guys at least understand what's the slow method. So first you do a DFS on the tree and basically give each node a height. Let's say we start from 0. So this node's height is 0, this node's height is 1, this node's height is 1, this node's height is 2, 2, 2. You can get these heights by a DFS or something. Right, I'm just putting all the heights. Now, once you got, so obviously I'm expecting everyone knows the definition of a height here. It's pretty intuitive. How much, like, what's the distance between you and the root? How far are you from the root? And this is the root, right? So now the question becomes that this is u and this is v. Now the algorithm for a slow LCA, slow lowest common ancestor finding, is basically take the out of u and v. Let's say you have u. Okay, let u dash be u, let v dash be v. Now, whichever guy is deeper in the tree, make him climb one step up. Okay, so you can unmute yourself in between if you want to, and also you can post your doubts on the chat, and I'll obviously reply to them. And because I'm sharing on iPad, you can't see the other people's doubts, so I'll just I'll first say out the doubt here on orally, and then I'll also reply. Yeah. So the slow method is let's say you have u dash and v dash. Like let's say you start with these two variables, which are u and v itself, and then whichever guy is the deeper guy here. Deeper means which has more height, who lies at the bottom of the tree out of these two, will climb one step up. So here v is like lower than u, so yeah, so v will climb one step up and come here, right? Once he comes here, so u dash will now be again this guy u, and v dash will technically be parent of v, right? And now once we are at the parent of v, then we'll again compare the heights of the two guys. His height is 3, his height is 3. So now we can arbitrarily pick anyone and just climb them one more step up again and keep on doing this. And what's the breaking condition? The breaking condition is when both the nodes u dash and v dash are equal. That's the breaking condition. So in terms of pseudocode, it will look something like, okay, also I forgot to mention this one thing, that with the heights, you'll also have parents. So this guy will know that his parent is -1, which is basically nothing. This guy will know that his parent is this guy. This guy will know that his parent is this guy, so on. I'll give a more concrete example. So I didn't label the tree nodes there in the other tree. Let's label the nodes here. Okay, so let's say this is our tree, right? And we are trying to find the LCA of 7,12. So this guy and this guy, right? Okay, quickly get the heights of all the guys. I won't put all the heights. I'll just do something like this. I mean, otherwise the diagram becomes pretty messy. So I'll just put the heights over here. But otherwise, you're actually calculating the heights of every node and also the parents of every node. So in parents, I can give you an example. This guy's parent is -1. So we put p equal -1 here. This guy's parent is 1 because basically the ID of the node who's your parent. This guy's parent is also 1. He's the parent, right? 4's parent is 3. 5's parent is also 3. 6's parent is also 3. 7's parent is 4. 8's parent is 4. 9's parent is 5. So on. 10's parent is 9. 11 is 9, 12 is 11, 13 is 11. Just see the parent and like put it there. And like in a DFS, I'll just show in the code how you actually get the parents. It's reasonably simple. Now the code, like, okay, so you're trying for 7 and 12, right? Who is the deeper guy? Who has a more height? 12, right? He has height 5, whereas 7 has height 3. So you'll make him climb one step up. So he'll come to 11 now. Now you're comparing. So basically the problem of finding LCA of 7,12 got simplified to finding the LCA of 7,11. It's the same thing because once you climb one step up, it's the same thing. The LCA of 7,12 will be the exact same thing as the answer for LCA of 7,11. Now we'll again see in 7,11, who is the guy that's deeper? 11 is still deeper. 11's height is 4, 7's height is 3. So we'll make him climb one more step up. And now that goes to 7,9. Now we'll again ask whose height is deeper. Let's say because they both are heights are equal, 7 is also on height 3, 9 is also on height 3. So we'll just pick any of them. Let's say we pick 7 and we make 7 climb one step up. So now 7 will go to 4, right? Here. And so it becomes 4 comma 9. So you have these two pointers. One pointer starts at 7, the other pointer starts at 12, and gradually they both move up. So this guy keeps on moving up, and this guy also keeps on moving up. And the rule for moving is whoever is deeper gets to move, and whoever is deeper gets to move. And because of that, they meet for the first time at the lowest common ancestor itself. So once you're at 4 comma 9, who is the deeper guy? 4's height is 2, 9's height is 3, so 9 will move, right? And 9 will move to 5, so 4 comma 5. And once you're at 4 comma 5, both the heights are again equal, so you can move any of them. Let's say you move 4 again, so it becomes 3 comma 5 because 4 went here. And then in 3 comma 5, 5 is deeper, right? 5 height is 2, 3's height is 1, so 5 will move one step up and he'll come to 3 comma 3. Now you'll stop here because these two nodes are equal. Here at any of the previous stages, both the nodes never became equal, so you would never stopped. The terminating condition for this algorithm is that both the nodes became equal. Once both the nodes became equal, this is the LCA. So 3 is the LCA, that's it. 3 is the lowest common ancestor. So in terms of code, the rule is something like this. While u not equal v, if height of u is greater or equal height of v, then we say u is equal to parent of u. Otherwise, we say v is equal to parent of v. That's it. And eventually, LCA is equal to u. That's how simple the code looks. When we reach 7 comma 9, why didn't we go to 4 comma 5 directly? Okay, someone asked me this. Okay, let me see. We are at 7 comma 9. Why didn't we go to 4 comma 5 directly? Okay, you can go to 4 comma 5 directly. Technically, you know that both of them are at the same height and they're not the same. So both of them do have to climb up. But I mean, just the algorithmic implementation is in such a way that you do it step by step. So in one step, you only move one guy one step up. But if you wanted to, you could do this. Like example, you would change. How would you change this code if you wanted to do what you said? You would do this and then else if h. So he basically said that if both the guys are at equal height, we can just move both the guys together. And otherwise, like we'll have one more else, which is basically they're equal. Then we'll say u is equal to p comma u comma v is equal to p comma v. Right? Even this will work. I mean, it's still, this is also correct. It's just like slightly more code, and yeah, might be a bit confusing, but yeah, it's correct. That if both of them are at the same height in the tree, like here 7 and 9 are at the same height in the tree, but they are not the same value, so you can move both of them up. You know that both of them definitely need to move up to find the LCA. So basically, the idea of picking the deeper guy and moving him up is that you're definitely sure that he needs to move up to be able to find the LCA. Let's say you started at 7 comma 12. You can't move 7 up in the first step. Why? Because let's say 12 was actually somewhere here. Like there was, okay, I mean the diagram gets dirty pretty quickly, but let's say this was the tree, right? This was 7, and let's say this was 12. Now, had you moved 7 up earlier, you would have already lost. You would have already made the answer incorrect because the LCA technically is 7 itself. For 7 and 12, who is the lowest guy who's common to both of them? 7 himself, right? So that's why you always move the deeper guy up, because if you move the shallower guy up, the problem is that you sometimes might just skip the answer and go above the answer. By above, I mean you go above the height at which the answer can lie. Are you changing the data? Anupam asked, are you changing the data structure to move to parent, or are you finding parent for each node in each run? Okay, Anupam, we earlier said that in a one DFS, we'll do a DFS originally, like one DFS, in which we'll find heights of all the guys. Here at the I put as heights, and also the parents of all the guys. So literally, there will be a height array and a parent array, and we'll fill this array using one DFS. And after that, for each query, let's say we got a query 7, 12, we can find the answer in ON using this algorithm. I mean, I'll just write the simpler version here because one more line. LCA is equal to U. Yeah. Using this algorithm, we'll find the thing. Abhishek asked, is this the slow method or the fast one? This is the slow method, Abhishek. Because look at this. This is actually running pretty slow. And like in each step, we are just climbing one parent up. So think about the worst case of this algorithm. The worst case is, let's say I give you a tree in which one guy lies at the very bottom, okay, and the other guy lies at the extreme end. These two guys are the U and V. Then you'll take and rough like let's say this is n by 2 and this is also n by 2, the height I'm referring to, right? Then you'll take n by 2 steps to come here and n by 2 steps to come here, which is the LCA. So this will take order n. Like in the worst case, this algorithm will take order n. Okay, Abhish, yeah. So technically the tree can be of any height. That's why it's slow, because like if you're very far from the LCA, you'll take a long time to go to the LCA. Let's say this is the LCA and this is U, this is V. You'll take a long time if these two distances are big, right? Okay, so now the fast method. So the idea of moving the deeper guy up still remains the same, that we'll move the deeper guy quickly. Okay. One thing that now we want to do is we want to do a binary jumping thing, which is we want to move fast. So, okay, how should we go about this? Let me think. Let's say this is U, this is, no, let's say this is U, this is V, right? Yep. So, okay, I'll explain it this way. Yeah. First, okay, don't think about the tree that much. Like, okay, just think about the slow method. That's the important thing. In the slow method, notice what was the first step. The first step was, let's say you have height of U as 10 and height of V as like, let's say a very big number, 40. The first thing that you did was indirectly moved V to its 30th parent such that, okay, and let this parent be V dash, 30th parent of V, such that height of V dash is 10. Basically, you move the deeper guy up so much that both of them become of the same height. And then we do step-by-step thinking, right? Like in this algorithm, notice, let's say V is of a very big height. Then this else condition will be triggered a lot of times for the first few iterations. And once they both become equal, then one step will take U, in the next iteration, V will take one step and so on, till the time they become equal. So like if you just think about this algorithm, what's happening is that the deeper guy, which I'm assuming is V, is getting moved a lot of times to match till the height of U, and then they both are moving together step by step, right? So let's say, yeah, can you do this movement fast? That's the first question. Like let's say we know that the height of U is 10 and we know that the height of V is 40. Now we want to find the 30th parent of V. Can we find this 30th parent of V fast? Okay, that's the question. So notice that to find the 30th parent of V, you can say, I'm trying to find the break 13 powers of 2. So what is 30? 30 is 16 plus 8 plus 4 plus 2, I think. 24, 28, 30. Yeah. So this much parent of V, that's what I'm trying to find, right? And I can say, I know what's the 16th parent of, okay, now comes the magical part. So in the tree, originally, what we were doing were that we were just maintaining the parents, right? This guy knew his parent, 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 etc. Right? Now we'll maintain some extra information also, which is like slightly tricky. So just try to understand this part as much as better as you can. In this kind of question in the given tree, can any two nodes have the same value? Yes, then how to identify whether they are communicating? I mean, no, the nodes cannot have same value because you're considering the nodes as having labels. In any graph question you do, no two nodes can have the same node ID. I'm talking about the node ID. I'm not talking about the value. Each node might have a different value. Like maybe the question is like each node is, let's say, a city. So each city is different, but maybe cities have populations and like two cities can have the same population. But here what we are trying to compare on is the city name or the city node ID, which has to be different. Yeah, it's a good question though. So yeah, let's say we have this tree, right? Originally we just had the parent array. Kotaburi asked, why are we taking power of 2? I'll explain this later. I'm not trying to explain it now. It's pretty tricky. I mean, it's the same logic as like squaring, power, like binary exponentiation or binary search. In any algorithm, you never take powers of 3 or powers of 5 or something, because the log n factor becomes worse. Like if you start taking some different power, the complexity becomes worse. So that's why people generally tend to prefer the binary breakage. Yeah. So like, okay, now let me concentrate. So originally we had this information that each node knows its parent, right? Now we'll have this extra information that each node knows its parent, okay, second parent, okay, fourth parent, eighth parent, and so on, every power of 2th parent. Okay, so the idea is like PUI will denote who is the 2 to the power ith parent of U. This is what PUI will denote. This is a very important definition. I mean, in like lowest common ancestor fast. In a binary tree, the edges are directed downward, right? I don't understand how we can move upwards. You're not okay. You're just maintaining who is your parent. That's it. In a DFS, in a single DFS, you just maintain that, and like now you can move up because you know who's my parent. Like you already, like in this tree, node 5, like somewhere in the array, P of 5 was stored to be 3. That means 5's parent is 3. This was stored after the single DFS. So now when we are at 5 can just look at this value P5 and know that, okay, my parent is 3, I can just move up. Like technically you're not moving up, you're just changing the variable. You're just changing the variable V to its parent's variable, its parent's node ID. Like obviously this is just a visual representation of what's happening, but like only the variables are being changed actually. Yeah, so you have this 2 to the power ith parent of U, right? Now first forget how you construct this. Let's say we have this somehow. So I'll give you an example. This is a factory because I don't have IDs. Let's have 1, 2, 3. I'll make a very like deep tree because I want to show what all information will be there. Okay, so now here example, parent of 11 0, P11 0, what will it be? Like can anyone answer what will P11 0 be? Here is 11. I want to see whether people get the definition. Like according to this definition, who will be P11 0? First parent of 11, yes, 10, correct. And what will be P11 1? The second parent, which is 9. And P11 2, the fourth parent, which is 4, correct. Yeah, so everyone got this, right? That what am I trying to store in the P11 array? P11 3 will be by default, I think it'll jump up. So by default you try to keep it -1 or 0, like some default value. I generally keep it, I think 0. I generally keep it 0, but that's an implementation detail. And then all the future ones also will be 0, right? So that's like, okay, now everyone knows that what our PUI array will look like. Forget about how we construct this, but I will like explain later that we can construct it in n log n time, this entire array, once we have done the first DFS. Once you have this array, the idea is, let's say you are doing a lowest common ancestor of 6 and 11. Then you say, what's the difference in their heights? Okay, so this guy's height is 0, this guy's height is 1, like these guys. This layer is 2, this layer is 3, this layer is 4, this layer is 6, sorry 5, this layer is 6. So what's the difference between the 6 and 3? 3, right? So the difference in the heights is 3, right? So we'll say we want to make 11 climb 3 steps up, which is basically to 7, but like that's what in code we are saying, that we want to climb 11 3 steps up. Now we don't have this information directly, that how will we climb him 3 steps up. So we say break 3 in its powers of 2, which is 2 plus 1. Okay, and then first make him climb 2 parents up, which is from 11 you go for 2 parents up. What is this? This is 2 to the power 1 and this is 2 to the power 0. So 1 here. So you refer to this position, right? And you just go to 9, 2 parents up. You have this information stored here. And then from 9, you'll ask go 1 parent up, because this is this. P11 to 11 greater than 10 greater than 9 greater than 7. I mean, why I don't understand why you use the greater sign, because technically the node IDs can be jumbled. But yeah, otherwise it's correct. Yeah, the idea is correct. That, okay, not okay, go to. Okay, no, P11 2 technically just means that who's the, sorry, P11 2 technically means who's the fourth parent of 11, right? Which is 4. P11 2 means the fourth parent of 11. Why? Because P11 2 stands by this definition, which is who is the 2 to the power 2, which is 4, the fourth parent of 11. So that's just 4. You don't really store the path, you just store who is it. Okay, so we were at 11 and we wanted to jump 3 steps up, right? And we said 3 can be broken as 2 to the power 1 plus 2 to the power 0 in its binary representation. So we said first make 2 to the power 1 sized jump from 11 and you come to 9. Now notice you have a P90, a P91 also. Can anyone tell me what the values will be? You have this entire thing for all possible values of u, right? So it's n possible values of u and log n possible values of I. So P90 will be 7, correct? And P91 will be, for example, 4, and so on. You can calculate all of these also if you want. Like they will be calculated. Yeah, let me make sure. So now once we have climbed 2 steps up and we are at 9, now we'll ask 9, okay, who's your 0th parent, like 2 to the power 0th parent. So we'll refer to this value and go to 7, and we are done. So does everyone understand how we nullify the difference? Initially the difference was 3 and now we killed the difference. How did we kill the difference? In generic terms. Let's say you had this big tree where u was here and then there were a lot of nodes and then v was here. Okay, there might be some other stuff here also, but like that's the important part. And okay, not the u was, let's say, here. So we wanted to climb v till this stage, right, to get the same height. The idea is take the difference of the heights. Let's say the difference of the heights is 12. Let's take a better example, 13. And then break 13 in its powers of 2, which is 2 to the power 3 plus 2 to the power 2 plus 2 to the power 0. Right? 8 plus 4 plus 1. Then say, okay, for v, who is his 2 to the power 3th parent? So you'll say basically make v dash equal to parent of v comma 3. Then you'll say make v double dash equal to, so you'll move here v dash, which is 8 steps above him. Now you'll say make v double dash equals to p v dash comma 2. From v dash, you'll again move 4 steps up and go to v double dash. That's what this statement is doing. And then from v double dash, you'll say v triple dash is equal to p v double dash 0. 0 here because this is the binary representation. That's why I'm doing these specific jumps. And then you'll go till some node here, which is at the same height as node u. Okay, yeah, people are asking. Yeah, this method is mainly required if you have a large number of queries. Like if you're asked a lot of LCS of u comma v for different pairs, and for each pair you want to answer pretty fast because there are a lot of pairs coming in. So you want to do each pair fast, that's in order login or in order 1 or whatever. This method works in login. Yeah. So now once you've climbed till v triple dash, okay, then you can then you got 2 nodes at the same height, and then you can do the step-by-step method that we explained earlier, right? Does everyone get this part? How we nullified the height difference and got till the same step, got both the nodes at the same height, and we did this fast. That's also important to note, that we broke them in binary representation and then we just did log n steps here at most, because the height difference can only be at most n, and its binary representation will only have log n terms. Like the number of terms here will only be log n. Okay, I hope, like if anyone has a doubt here, they should stop me or ask it out on the chat. Is there a need to jump in decreasing order? Okay, nice question. No, not really. I mean, you could do the first jump as 2 to the power 2 sized, and then 2 to the power 3 size, and then a 2 to the power 0 size. You could do different size. It's not necessary for these 3 numbers to be in this order. You can even switch them around and it will still work, because it's saying you have a height difference of 13. Either you cover it 8, 4, 1, or you maybe cover it 1, 8, 4. Nobody cares. You just have to cover the difference. Distance. After getting equal heights. Okay. Why can't we directly jump to the same level? I mean, how will you jump to the same level? Like, I don't understand CodeChef team's question. You don't know the 13th parent of V. That's the issue. So you can't but you do know what's the 4th parent of V. You do know what's the 8th parent, what's the 16th parent, but you don't know who's the 13th parent. You've only stored limited information. Here you haven't stored all the parents, like the first parent, the second parent, so on of U. You've only stored powers of 2 because you don't want to waste a lot of time computing this also. Right? So you can't just jump directly to that same level. Even though you know you have to go to that level, but you don't know who is V's ancestor in that level. In this level, which node is the guy who is ancestring V? Well, there is only one guy in this level who is ancestring V, but we don't know that guy. So this is the way to find him. Okay. Devan, after this step. Okay. Sunny asked, explain the time complexity. So Sunny, the idea is for the time complexity at least, the difference in the two heights, let's say height of U is something, height of V is something, the difference can only be at most n, right? It will be less than equal n. And when you break it in its binary representation, you'll have only log n bits, right? So only 2 to the power some term plus 2 to the power some term, da da da. But only log n different terms you'll have. And for each term, oh, sorry, CodeChef asked me doubts from the YouTube session. Okay. For each term, what you'll do is basically you'll refer to your parents table and make a jump associated with that size. Can we do it recursively? Okay, in actual implementation, you will, I think most people prefer to do it iteratively, but you can do it recursively. And always check the UNV value. Yes, you will check the UNV value, but like whether they hit equal or not. Okay, let's go ahead in the question, like in the algorithm. I don't think we can waste a lot of time on it. I think everyone understood the idea that we have to nullify the difference, and to do that, we represent it in binary representation and then make the jumps, right? So now once we've killed all the difference, we know at this step that U and V might be at the same height, and like, okay, so now U and V are at the same height. They might be the same guy. That is, they are actually referring to the same guy. Example, let's say this was the tree. U was here, V was here. Now the height difference is 2, right? V will climb 2 steps up in order 1, and then U and V will technically be the same thing. So at that point only you should return it as the answer because they're the same thing. But otherwise, if they're not the same thing, that means you have this. So this is case 1, when this is a simpler case, that when V climbs up and they both become of same height, they're actually pointing at the same guy. So you just check if U equal V, return U. That is U is your answer, right? But what's the case 2, which is the tricky case? That is that they're not the same guy, but they're on the same level. That's it. That's the only information that you have. Let's say this is U, this is V. Now here, they're at the same height, but they're still technically not the same guy, but they're at the same height. So now, at this point, you like in the original question, you had some U comma V. Now in this question, you have a V U comma V, but you know that the height of U is definitely equal to the height of V. That's the additional information that you have right now. Yes, I'm explaining the LC problem. So how to do this, like how to solve this when they are at the same height, but technically 2 different guys, right? And you want to do it fast also. In the slow method, you could still do it in order n, that is like basically just make each person climb 1 step up, blah, 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 and wait till the time they hit, right? But we want to do this fast. The idea is that you have that parent array, right? You had this important parent array, which I'll refer to again and again. Like that's the key of this algorithm, this thing. You had this 2D parent array. Now in this 2D parent array, you can use this 2D parent array. How? You'll say, okay, intuitively think about this. What will PU of 10 be the same as PV of 10 in this above tree? Will they be the same? Yes, Anurag answered. Yeah, correct. Basically, if you take any big number here, what I'm trying to ask is 2 to the power xth parent of U, parent of U will probably match with 2 to the power xth parent of V. Right? If x is pretty big, like let's say x is 10, that means I'm asking 1 U versus 1000th parent of V, 1024th parent of U versus 1024th parent of V, which will be the same. Here notice the first parent of U is different for the first parent of V, but the second parents of both the guys are same. Right? So correct, Rockstar is correct that we need to do some sort of binary search here. So the property that you have is, let's say you have this thing that, okay. So basically the idea is, let me define something. Okay, let's define this. FUH refers to Hth parent of U. Okay, that is what FUH denotes. So FU0 is something, FV0 is something, FU1 is something, FV1 is something. Hth parent, okay, sorry, it's the hth parent, but technically there is no zero. First parent, so FU1 basically denotes the first parent. FU2 denotes the second parent. I'm not talking about powers of twos here. I'm just talking about the hth parent. That's it. Not the 2 to the power hth parent. This is a simpler definition. Okay. And then f of v comma 2, f of u comma 3, f of v comma 3, and so on. Notice at like initial values they will mismatch, but at some point they will become equal. Let's say the f of u comma 6 and f of v comma 6. Once they become equal, they will always remain equal. Can everyone see this? Like intuitively, that why they'll mismatch for the first bunch of times, for the first few times, and then once they become equal the first time, they'll always remain equal. The idea is this. Like, why am I saying this? Let's say you had this tree. This is U, this is V. Now the first parents mismatch. This guy mismatches with this guy. The second parents mismatch. The third parents mismatch. I messed it up a bit. Let me draw it again. So the idea is this. Let's say you have this tree. I'm not drawing at the same height technically, so that's an issue. Yeah. So this is U, this is V. Now the first parents are different, right? The second parents are also different. The third parents are also different. The fourth parent is the same. Now, once the fourth parent became the same, it's obvious to see that the fifth parent will also remain the same, the sixth parent will also remain the same, the seventh parent will also remain the same, so on. Right? Because once they become same, technically moving one step up for both of them is the same thing. Like here, you will also move one step up, we will also move one step up, but they'll still point at the same thing because both of them are the same node. Right? So everyone agrees with me that this property will be true, that for some time, for the first few parents, we'll mismatch, but then for the first time when we match, we are done. And we want to find this position actually, the first position that they match. That's the LCA. Here, the LCA was the first position that they matched. Their parents matched the first position, not any position, but the first position. So this is a binary searchable function in the sense this value is a mismatch. Like it's monotonic in the sense that you're getting a few mismatches and then you're getting a match and then you keep on getting a match. Everyone agrees with me that this is binary searchable in some sense, that there are few mismatches first and then a mismatch, and we want to find this first match. Okay, so there is a log square n approach to do this using binary search and another complicated thing, but I'll just directly go to the log n approach because that's a simpler idea. The idea is it's slightly different from the standard binary search that you guys see. The idea is you start with a very big power of 2 and then you keep on chopping it. Let me explain this way. Let's say this is the LCA. Okay, it has a bunch of parents above it. We don't care about this portion, and it has a bunch of guys below it, and then U comes here, and then V comes here. There are a bunch of guys in between. We don't care, and there are a bunch of guys in between. We don't care. But the heights are same of U and V. Okay, we don't care about the height also. To be honest, yeah, we don't care about a lot of stuff. But that's the generic structure, right? U and V will be 2 nodes. There will be an LCA and there will be some parentage of LCA. That's the generic thing that you always look for in an LCA question. That's how the tree looks. I mean, just ignore all the other parts. Even though there are other parts, just ignore them mentally. because you know that you won't use them. Now, the idea is take a very big power of 2, the highest power of 2 that you can take. So let's say n is 100. Then what's the highest power of 2? Just exceeding this or something? We want to exceeding. No, 64 is the highest power of 2, right? Just below it. So, which is 2 to the power 8. So you'll say PU8. Does it match with PV8 or not? That's the question that you'll ask. Does it match? If it matches, then you say we climb that much up. Okay, 100 is actually a pretty big example. I shouldn't take that because otherwise it's going to be very exhausting for us to understand the technique. I'll take a simple example. Rahu, I'll explain this later. I haven't explained it, I know this. I'll explain this later, that how we populate the values. It's a simple recurrence. You'll get this quickly if you know basic DPs. Let me go for an example, like to explain this. I'll take the values as, okay, yeah. Let's say this height difference is 13. Yeah, the 13 is a good number here. Yeah, let's say this height number is 13. Okay. Now, and let's say the total height of the tree, like, okay, n, let's say n is going to be pretty small. That is, n is, I don't know, 50. Yeah, say n is 50. Okay. Now, below 50, what's the highest power of 2? 32. So you'll say, is PU5 same as PV5? You'll ask this question. Are these two values same in your algorithm? They will be the same because technically after the 13th parent, everything matches. So the 32th parent, that is, this is basically FU32, right? And this is FV32. And we know by a fact that FU13 will start matching with FV13. Let's say I already tell you the answer. Obviously, you don't know this information, but had we known this information, we know that this will match. Because this matches, we drop from 5 to 4. Okay, so now we ask the same question for 16. That is FU16 the same as FV16? Are they the same? We ask this question, and yes, they are the same again, because after the 13th parent, everything matched, right? Now we again dropped one more step. So from 5, we went to 4. Now from 4, we'll go to 3, like 2 to the power 3. That's the idea. So in binary, we are going decreasing. Okay, now we ask, is FU, my battery died. So okay, the thing's battery died. So meanwhile, I'll explain some portion on the editor, like till the time it charges. I think it'll take like 15 minutes or something, 10 minutes maybe. Okay, so I'll go through the first part of the implementation. Okay, that is, how do we write the, everyone can see the editor screen, right? I'm assuming everyone can. I disconnected from the discussion because my iPad's battery died, like the pencils, the stylus. I'll go through the I'll go through the code up till the point that we have explained till now, not beyond that portion. Okay. Like, so how will the question look like generically speaking? The question will have a tree. Like, okay, and tree is generally given in this format in most questions. Okay, let's actually follow the keys. I can't switch. Yeah, let's follow this. T-test cases. I'll try to write some portion of the code for Enoch 1. I don't want to waste time waiting for it to charge, so I'll just like do something and like show people. We call the solve function. Yeah, I'm assuming everyone can see the screen. Okay. The Enoch question is pretty simple. It's just like you're given a tree. Each node has a value which is a of I, and then you're given a bunch of queries, right? And in each query, you're given 2 nodes, and you have to find the LC of those 2 nodes. Sorry, the cost aggregate of those 2 nodes. So let's say I calculate there int LC equal LCA, x equal LCA of 2, B, and then I say C out x of second. then this is a pair int LCA int u int v. So the idea is that this pair should return LCA comma aggregate from u to LCA and LCA to v. Okay, this is what this pair, like this function, should return. So we have this function. First line of each test case contains 2 integers. Okay, then we also have this in the input, which is the tree itself. Everyone can like see what I'm trying to do, right? I've created an adjacency list. I'm filling the adjacency list with the trees information, whatever I get, and then I'll do a DFS from node 1. Okay, the nodes are labeled from, I'm assuming 1 to something. Yeah, the nodes are labeled 1 based. So now I'm doing a DFS. In the DFS, notice what all information I'm trying to keep. So I'm maintaining the heights, right? And the height has a very simple recurrence, which is, okay. Also see n was 10 to the power 5. Now for 10 to the power 5, what login should you use? Anything over 2 to the power 20 sounds good, right? I mean, 2 to the power 20 is 1e6, around 1e6. So anything above that sounds good, right? And now what we'll do is we'll do a loop on the adjacency list of u in the DFS. I'm assuming everyone is familiar with the basic DFS. I'm just writing a standard DFS. If v is equal pref, we continue because we have bidirected edges. Like it can be the case that we are at a node and we just saw the parent. I haven't seen the Navjot, I haven't seen the lunchtime question. I can't help very much. Otherwise, what we'll do is we'll do a DFS recursively, right? So now we have this height array and we want this parent array. This is the parent array that we were talking about in the question. That's the the most important array, right? That we were referring to constantly. Shouldn't we have visited vector? You don't really need a visited vector because I'm doing, okay, in graphs, okay, so this is a good question for generic graphs. In normal graphs, you need visited array for sure. In trees, you can do without it also. Because notice my check for whether I'm not going into something again and again is this. If v is prev, I'll just continue. Yeah, I mentioned that correctly. Right, if v is prep, then I'll just continue, and like basically I won't go into the recursion again. So you can try to think that if this function will actually not keep on visiting the same nodes again and again. Okay, so in the DFS we have this height, right? And then okay, now what all information can we store again apart from this? We can easily store what will the parent of u will be, like the 0th parent, that is the normal parent of u will just be pref, right? What will be the other parents? So this is an important thing. This is like probably the part that people were referring to, how calculating p u, right? How do we calculate this array? This is the recurrence is pretty simple. It's just this: pui is equal to p of pu I minus 1 I minus 1. Ta-da! Okay, this is slightly tricky to get, and the first time you see this, the idea is what? Okay, I'll try to explain this way. Int half jump equals pu I minus 1. Int second half jump is equal to p first half jump I minus 1. That's the idea. So let's say you're calculating pu5, that is 32th parent of u. You can say 32th parent of u is equal to 16th parent of 16th parent of u, right? It's the same thing. Like basically climb 16 steps up and then ask that guy who's your 16th parent. So this thing, the 16th parent of u, becomes first half jump. Basically, I broke this 32 size jump into two like half jumps. First jump is climbing the 16th parent of u, which is this thing, right? I'll just take the I-4 one, which is basically pu4. And then I'll ask, okay, I'll ask the first half jump guy who 16th parent of the first half jump guy, right? This is basically p of first half jump 4. And this is my kind of final answer, PUI. This is the second half of the jump. So when I make the two halves of the jump, I just got the 32th parent. Like this guy is going to be actually the 32th parent of u. Everyone gets this part of how I calculate it. Okay, this is slightly tricky. So to calculate the 32th parent of u, I say it's same as asking who's the 16th parent of 16th parent of u. So I say, let's say the 16th parent of u is some guy. And if I go to that guy, I can again ask that guy, who's your 16th parent? If he tells me the correct answer, I can just go to that guy and I'm done. Like a node's 32th parent is equal to saying, first jump 16 steps up and whoever guy you find at that position, ask him who is his 16th parent. And that's my 32th parent. Okay, example. Let's say V is 16th parent of U. Okay. I'll just draw this rough sketch so that people can get this idea. Let's say this is U. No, sorry. Let's say this is X. This is V. This is U, right? What I'm saying is, and let's say the distance between U and V is 16 and the distance between V and X is 16. What I'm saying is, you will ask, who's my 16th parent? That will come out to be V. So here, 16 parent and like 16 parent of U will actually be V, right? Which is PU4. And then 16th parent of V will ask again, this will be X. So I jump 16 steps up by using PU4, and then from V, I again jump 16 steps up to get me X, which is PVX. I'm not sure what Nilesh is asking for. Nilesh is saying, please also explain LCA using linked list. I'm not sure. I don't think there is any concept of linked list here. On trees, generally, you don't have any concept of linked list. I mean, you store the entire tree in a adjacency list, which is a vector, and then yeah, I'm not sure what you're talking about. I don't think there is any linked list thing. How do we have the 16th parent? Okay, we have the 16th parent because we already like look at this looping structure, right? We've already calculated the 1, the 2, the 3, the 4. So when we are calculating for I equal 5, we have already calculated for I equal 4, right? So we already know PU4. We know this. You get this part? We already know PU4. And also, okay, because, okay, I'll write this at some place simpler and like slightly different way. I'm confident that some people like might find this right now confusing. You can do this like this also. PU0 equal pref. Okay. Now this is the height variable, which is going to log in. After the DFS, I'm doing this. So once the DFS is done, we only have the immediate parents. We only have this thing, PU0. That's it. We don't have anything else. Then we'll take each height, and for that height, we'll iterate over all the nodes. Okay. And once we're iterating over all the nodes, we'll say Pji equal Pj I-1, I-1. Yeah, which is basically saying, I mean, the pseudo code was this. pji minus 1 and pji equal pv minus 1. Make what are the prerequisites of this class? Unless the prerequisites are going through the content of graph theory week, which is like DFS, BFS, adjacency lists. Yeah, at least that much. Adjacency list requires vector knowledge, and like basic recursion. DFS requires basic recursion, etc. Yeah. So, do people get this part, line 59? Like, just reply yes, no, or whatever in the chat. Because if people do understand, okay, can you please explain why this ordering works? Okay. Yeah. Okay. Nice question. The ordering works because I put the I loop outside and the J loop inside. Notice this. I did this because the idea is calculating each height layer requires you to know this stuff. Okay. Notice this part. This line V equal Pji minus 1. Now, had you switched the order of these two loops 55, 56 on line 55, 56, the issue would be that you might not know this value V Pji minus 1 because, okay, let's assume that we had switched these loops. Okay. Now notice when you're referring to this value, okay, it's possible that J is bigger. Sorry. Okay, you'll calculate this value correctly, probably. Yes, you'll calculate this value correctly. But notice when you're calculating this value, it is possible that V is greater than J. Right? When V is greater than J, the issue will be that your J is still here and you actually don't have the value PVI minus 1 with you. You don't have the correct value. So that's why you need to make these like these. Okay. Yeah, I'll explain this through code also. Okay. I think the battery thing should be done now. Not able to understand from DFS. Okay, Devansh asked, Devansh, could you explain your doubt more? Like not able to understand from DFS, what do you mean? I mean, do you understand the current DFS? This is a pretty simple DFS. You're just calculating the heights, then you're calculating the parents, immediate parents, that's the 0th parent, not anything else. And then if you're at, like, if you're referring to some previous guy, then you're skipping him. Otherwise, you're just going inside him. Yeah, so current DFS is simple. If you wanted to, okay, after the DFS, this portion, is it? Oh, not able to understand from DFS. Okay, after the DFS, okay, I'll just go through to the iPad once more. Yeah, it starts probably. Yeah, it starts. So I'll explain it through that. I think it's simpler visually. I mean, I get that this is. Yeah. Okay. Can people see the maybe tell a lot of and used to explain this? Don't overkill so much. I mean, it's a tree. You don't really care about topological sorts or anything. It's a tree. It's not a graph. Don't think about, like, for trees, just try to keep things as simple as possible. For graphs, yes, you do need concepts like topological ordering and stuff. For trees, you don't. Yeah. Okay. So we were here, right? Okay. I'll continue from here. Then I'll explain how to fill the P array. So FU16, FV16. And this also matched because recall that we were saying that this is height difference is 13. Everyone remembers this, right? The height difference was 13 between these two guys. So we checked height 32, then we checked height 16, and both of them matched. Then we went to third. So we say, what is f of U8 versus f of V8, right? And U8 and V8 were basically meant 8th parent of U and 8th parent of V. This will not match. For the first time, we are actually picking a position where they don't match. So because these guys don't match, you can actually move U 8 steps up and V 8 steps up. Do you get this idea? That take the highest power of 2, which is 32 in this case, because n is 50. Keep on dropping it. And the first time you find a place where these two guys don't match, make them jump that much. So now I'll make U jump 8 steps up and make V jump 8 steps up. So right now the tree looks like this, right? How will the tree look after the 8 jumps? There'll still be this LCA node. And then out of 13, I've killed 8, right? How much is left? 5 is left. So U is here, V is here, and sorry, this distance is 5 and this distance is 5. Right? The question that's going on is how to find LCA first. Yeah. So both these distances are 5, right? Now we have to make a jump of 5. So again, after 8, you go one step more, 4. Are their fourth parents same or not? These two guys. They're not, right? Because this is the fourth parent of this guy, this is the fourth parent of this guy. They're not the same. So height of U comma 4. Okay, technically we are not referring to U now. We are referring to U dash, which is basically U is somewhere here, U dash is this guy, V dash is here, V somewhere. Yeah, U dash is here, U is somewhere here, right? This was 8 sized jump, and V dash is here, V is somewhere here, and this was also an 8 sized jump. So after dropping from 32 to 16, then to 8, then we'll drop again to 4, and we'll ask the same question. Is f of U dash comma 4 the same as f of V dash comma 4? Are they the same or not? Can anyone answer this? In this question, U dash, V dash, H of U dash 4, H of V dash 4. No. Okay, Divakar, this is LCA, how to calculate lowest common ancestor first. Yeah, correct. So they're not the same, right? And because they're not the same, you'll again make this jump. Basically, you'll keep on jumping in decreasing power of 2s till the time you get to see that, okay, they're not the same, they're not the same, they're not the same. So I'll again jump. So this goes here, 4 steps up, this goes 4 steps up, right? How will they look now? I'll just make the tree again and again because it gets pretty dirty quickly. Right? U and V will just be one step away from the LCA after this jump. Okay, technically this is U double dash, this is V double dash. Now after 4, again decrease by power of, like again decrease the power of 2, which is 2 now. So I'll ask again the question, f of U comma 2, is it the same as f of V comma 2? Yes or no? Sorry, U double dash, V double dash. PU2 is 4 steps, but FU2 is just 2 steps. This 2 is not referring to 2 to the power 2. This is just referring to 2, the value 2. Yes, they are the same, right? So you won't jump because that's what we were doing here also. When the values were equal, we just used to decrease the power of 2, but we didn't actually jump. When we mismatched, then we used to jump. Here we mismatched. Here also we mismatched. But here we are equal. So we won't jump and just decrease the power of 2. So from 32, we came to 16, then we came to 8, then we came to 4, then we came to 2. Now we'll go to the last power of 2, which is 1. And ask, is f of U comma 1 equal to f of, sorry, I again keep on saying U, but it's actually double dashed. Yeah. Are they the same? Yes, they are the same, correct? They are the same. So again, we won't jump. Till the time they come out to be the same, we won't jump. And that's it. The algorithm terminates. Once the algorithm terminates, what we'll do is, we got to know this important information that, okay, now here's the conjecture. Once this algorithm terminates, you'll definitely be one step away from the LCA. The U dash, the U whatever value, U double dash, triple dash, whatever, and the V double dash, triple dash, whatever, they will just be one step away. So the final answer will just be return P U double dash 0. It's guaranteed that this is the conjecture. It's guaranteed that this is the LCA at this position, at this time. I'll give you an example, okay, to make this more clear. Let's say we want this to be the LCA, and let's say we want the distance to be, I don't know, how much do we want? We want a jump of size 8, then we want a jump of size 2, then we want a jump of size 1, 11. Okay. Oh, that's pretty big. I can't do that big. Okay, let's say a jump of 4 and then a jump of 1, 5. Okay, 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5. Okay, and let's say there's a lot of things above it. Okay, a lot of things. Blah 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 blah. And this is the U, this is the V. Now what will happen? You'll first ask who is the 32th parent of U and V. So they'll be somewhere here. Use 32th parent, V 32th parent. They will be the same. You don't care. You jump. You decrease from 32. You go to 16. Now you'll ask who's the 16th parent. Again, somewhere big, somewhere above. Skip 8th parent. Okay, notice that this difference is actually 5. 8th parent will also be somewhere above, right? Skip. 4. Notice FU4 is actually different from FV4, right? FU4 is this guy. FE4 is this guy. They're actually different. So you'll actually make the jump. So you'll jump till here. So now U dash will become this guy, V dash will become this guy. Once we are here, now you'll ask, after 4, you'll ask 2. So for U dash and V dash, you'll ask who are their second parents, which is this guy, right? But they are the same. So you won't jump. You won't do anything. You'll just skip this. Now you'll go 1. Who are their first parents? You'll see this guy, right? They're again the same. So you will skip this. Notice again, you ended up being at the position that's just 1 step away. So now again, you can return your answer as PU dash 0. I mean, right now I picked a very cute value, which was like 4 plus 1, 5, the difference being 5. Let's say you picked some other value. Let's say you picked, I don't know, 19, which is like 16 plus 2 plus 1. What will actually happen is you will be here, we will be here. And the distance till the LCA is 19, right? This is the LCA. When you do a 32 jump, you'll exceed this, so you won't make that jump. When you do the 16 jump, you'll actually make that jump and come here, right? And then after the 16th jump, you'll try to make the 8th jump, but you'll exceed this. You'll try to make the 4th jump, you'll exceed this. Then, because this difference is only 3 remaining push, then you'll make a jump of size 2, you'll actually be able to make it. So you'll come here and you'll come here, right? And then you'll try to make a jump of size 1, but you won't be able to make it because you're at the same position. So again, you ended up being 1 step away from the LCA. That's a common property. Do people try, like, can people see this property in this algorithm? That you keep on decreasing the power of 2 whenever the first time you mismatch on your parent's identity, you jump that much. Example with height of even number. Okay, good question. Yeah, we should do more examples. Just get the idea. How much would be 20? Okay, now 32 will again match, right? Somewhere above. 16 will mismatch. So let's say we come here and this guy comes here, right? After 16, 8 will match. So we skip it. 4 will also match. Notice 4 is the exact LCA. This was 16 and this was 4. 4 is the exact LCA. We'll match. So we won't jump that much. We'll now from 32, we went till 16. Then we went till 8. Here we, okay, at 16, we made the jump. At 8, we didn't make any jump. At 4, we didn't make any jump because, yeah, at 4, we didn't make any jump because like if you jump 4 steps above, they both are equal at the very LCA. So you can't make that jump. The rule is you'll only make the jump if the parents are unequal, if the jumping positions are unequal. So at 4, you don't make the jump. Then you go till 2. 2, you'll make the jump. So you'll come here and you will come here, right? And you, how much have you consumed? You have consumed 16 and you've consumed 2 on both sides. Now after 2, you'll go 1. You will again make that jump because you'll come just 1 step before. Notice for 20, what happened was we made the 16th jump, we made the 2th jump, and we made the 1st jump. So we actually made 19 in total, right? 16 plus 2 plus 1, we made 19 in total. Whatever your height difference is, like let's say this is 20, then you'll make 19 in total in this algorithm. And then eventually you just need to go 1 step above that position to get the LCA. If this is the odd number, let's say 25, then you'll make 24 in total. You'll always make 1 less, but that's no issue because you know that you'll make 1 less. Maybe to find the kth common ancestor. Kostab is asking, okay, Kostab, I don't get, we may be able to find the kth common ancestor. I don't get what you're saying. I'm not sure I'm getting the doubts here. Like they're very mixed. If you're writing a doubt, try to write it together because other people are also asking. Just like write it 1 sentence, like 1 para. What if the difference is power of 2? Then we will be 0 steps away, right? No, Devansh. Think about this. Let's say, yeah, this is also a good question. Let's say you're 16 steps away. Now you'll try 32 steps. You'll match. So you won't do that. You'll try 16 steps. You'll again match. You won't do 16 also. You'll actually do 8. right? 32 won't jump, 16 won't jump, 8 will be the first time you jump. And then after 8, you'll jump 4, then you'll jump 2, then you'll jump 1. This algo is for LCA. That's the lowest common ancestor. You're not trying to find the kth ancestor or anything. Yeah. I mean, you could use this parent technique for other things also. Yeah, we can modify it. Yeah, correct, Surendra. We can modify it to reach any ancestor. Because if you want to reach the kth ancestor, just break k as powers of 2 and then just keep on going that much. Like for each power of 2, just jump accordingly. In all these cases, the heights were same. Yes, Nischay. The heights were same because we had originally assumed, right? We did like a 30-minute discussion on this thing that when we were at mismatched heights here, yeah, in the fast version, we explained that when we were at mismatched heights, let's say the height of u is 10 and the height of v is 40, our step 1 was to make their height same. So we took the deeper guy and we said, how much do we need to move him up? So we calculated the difference and we said that much we'll move him up somehow. Like in this example, here was 6, here was 11. These two were the LCA guys, like the query guys. And the difference in height was 3. Right? 6 heights is 3, 11's height is 6. 6 minus 3 is 3. So we said we'll make 11 3 steps jump up. And to do this 3 steps jump up, we said break 3 as powers of 2 here and here. This thing. And then do the actual simulation of the jumps. So do people get this idea that once we are at the equal heights, we'll start from the biggest height, biggest power of 2, keep on going down, tuck, 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 tuck. And once we reach the first height where the parents actually start mismatching, we make that jump and we again keep on doing this. And like I tried to show it for a lot of examples. If it's still unclear, please ask. Because once I go into the implementation, your doubts won't be cleared. They can only become bigger. Like on the whiteboard, it's the best place to actually clear your doubts about the concept itself. Like how is the thing, why is the thing working? Once we start coding it, it won't remain easy. Surendra is asking, can you tell the log scoring approach also? Okay. I mean, I can tell it, but honestly, it won't be that much beneficial. Okay, the idea is basically this. So in here, we did this thing, right? That the first few F's mismatch. Where's the diagram? Sorry. Yeah. The first few things mismatch, then there is a match, and then they keep on matching, right? We did this. Okay, I'll first explain it for height 20. Yeah, cool. So this is this, right? This is height 20. Height 20. Right? Now, if this is 30, if you try 32 size jump, you'll skip, you'll match at the same thing, right? Because this is the LCA. Everything above is same. They'll match. The parents will match. So you won't try 32. Now you'll ask 16. So you'll say this guy's 16th parent, this guy's 16th parent. They are different. So you'll actually jump up. So this will be U dash, this will be V dash. You consume 16 spaces from here. You're only left with 4 here, right? After 16, you'll say 8. U dash's 8th parent will be above and V dash's 8th parent will also be above. So they'll match in terms of value. So you won't jump. At 16, you jumped, right? At 8, you didn't jump. At 4, will you jump? That's a tricky question. Because U dash 4th parent is the LCA, V dash 4th parent is also the LCA, but they are the same value. So you can't jump. That's the rule. So you again won't jump. You'll decrease the value again. 2, are their second parents the same or not? They are not the same. Because this guy's second parent is here, this guy's second parent is here. So you'll again jump here. And then after 2, 1, are their first parents the same or not? No, because there is one more guy here and there's one more guy here. So you consume 16, 2, 1. And once you're here, notice how much have you jumped. You have jumped 16, 2, 1. You have made 19 jumps in total. And you had to make 20. So you're still one step away. And that's the conjecture that you'll always, after this algorithm ends, you'll always be one step away. So at the end, you can just return the parent, the immediate parent of that guy. And that guy is the LCA. We can make a jump at 4, right? Devansh is asking. No, like, okay, you could technically, but our rule is very straightforward. Our rule is if the parents match, then we don't jump. So here, when we were at U dash and V dash, when we tried for 4, our 4th parents were actually the LCA itself. And LCA by definition is the same guy, right? U's fourth parent and V's fourth parent both are the same guy. And our rule is simple. If they are the same guy, we don't go. And we just decreased power of 2. So our algorithm was something like this. We took a very big power of 2, let's say h 2 to the power 20, okay, and we said while h not equal to 0, right, if PUH not equal to PVH, then sorry, h is not actually 2 to the power 20, h is just 20. Okay. I was using f everywhere, but you can use p also, right? Because we are only talking about powers of 2. We are not talking about anything else. If they're unequal, then we say jump u till its hth parent, jump v till its hth parent. Yeah, and then h minus minus. This is inside the if condition. That's the algo. It's as simple as that. After reaching 18, what we'll do? Okay, here in this example is a 20 example. I'm assuming you're talking about 20 example. So in the 20 example, once you make the 16 jump, and then you make the 2 jump, right? You're here. And this guy also made the 16 jump and the 2 jump. He's here. Notice your value of whatever power of 2 or whatever. It'll be at 2. We'll decrease it one more time and it'll become 1. Now you'll ask, who's the first parent of this guy and who's the first parent of this guy? Are they the same or not? They're not the same, right? Because LCA is here. There's still one more node in between. Because there is one more node in between and they're not the same, you'll jump. You'll actually do this jump. So eventually your U triple dash will be here and your V triple dash will be here after 1. And then 0 is killed basically after 1 terminates. Yes, Sunny, you're correct. We can only apply this algorithm after we have made the heights equal. I'm assuming both are at the same height. The step 1 was to make the heights equal and then we run this algorithm. Can you clear PU construction? Okay, nice. So everyone understands this part, right? The binary jumping part. After the same heights, you take the highest power of 2, and if they mismatch, you can jump that much. If they match, after 19. After 19, you don't jump because here notice after 1 gets terminated, and our conjecture was after the algorithm ends, U triple dash and V triple dash will be 1 step away from LCA. That's what our conjecture was. And our algorithm currently does hold on that conjecture. So this algorithm doesn't end at the LCA. Let's clear that confusion. This algorithm doesn't end at the LCA. It ends 1 step before it. But that's also good enough, right? Even if you end 1 step before it, you can just call, let's say you end up here. You can just call PU triple dash 0. And that guy is your LCA. This guy is the LCA. That's just the way this algorithm is implemented generally. That's why I'm saying that this algorithm doesn't aim to end exactly at the LCA. It just aims to end exactly 1 step below LCA. And then you can just do this manual climb in 1 step. Is everyone clear with this now? That in the simulation itself, I was always ending 1 step before it, not at the thing itself. But it doesn't matter because I'm sure that I'll end 1 step before it. So I can just do the last step myself. This is order 1. Okay, now we need the P construction, right? P array construction. So for the P array construction, the idea was this. Okay, how should I write? Tricky because people didn't get it. It's kind of like a DP if you think about it. Devans, this is a standard algorithm. Otherwise, it's very hard to come up with this. I agree. You can't. It's very hard to figure this out on your own. It's like now it's a reputed algorithm, so you know it for a fact that this conjecture happens. But coming up with it yourself is, I think, it's super hard. So Surinder asks, we stop at 18. No, you don't stop at 18. You stop at 19 because notice after 2, you still go 1 here, and then the first parent mismatch, and so you again end up here. You end up at 19, not 20. If the total size was x, then you end up at x minus 1 in this algorithm. Okay, when n is 19, yeah, sorry, yeah. If n is 19, you'll end up at 18. I can show it one last time. Like, let's say this is 19. You jump 16, right? But you won't jump 32 because it will go too far. Now, after 16, how much will you jump? You can't jump 4 because it will go too far because this is the LCA. So you can't jump 4 also. This jump can't happen. You'll jump 2. And after jumping 2, you can't jump 1 because again, you'll hit the LCA. So you end up here. That's it. So that's 18. I was mentally, I was doing 32, 16, 8, 4, 2, 1. I didn't show it this time, but yeah, we were doing that. Right? Why not 2 to the power 0? I mean, we did do 2 to the power 0. This is actually 2 to the power 0. In 20, notice our last jump was of size 1, right? Which is 2 to the power 0. I was just saying the power of 2, not the exponent, but like that is 2 to the power 0. You can't make the last jump actually, if you try to think about it. For N19, okay, for N19, we didn't make the last jump of size 1 because we were matching. The rule was that we'll keep on jumping till the time we don't match. If we are matching, we won't jump. That's the rule. I mean, obviously, Faisal, you can try to think about variants of this algorithm and it might work. That even if you do that, it might work. I'm not sure. But this is the most widely accepted thing. Like your method might also work that if you jump 2 to the power 0, you still might get the correct answer. But yeah, I'm just explaining the most popular approach. So now the P array construction. The P array construction comes from the fact, okay, think about this. Okay, so this will look like this, PNH. Okay, the first dimension will be the node. The second dimension will be I. Again, let's remind what's PUI. PUI refers to 2 to the power ith parent of U. Okay, this was the definition of PUI. Now, notice if we compromise space complexity, why don't we stop every? Okay, please ask on, don't ask privately because other people can't read the question and like I have to repeat the question orally, which becomes hard for other people. If we compromise space complexity, why don't we store every parent and get the answer in 2 moves? Okay, Anchit, okay, your idea is that we store every parent, right? But notice it requires a lot of space. How much space does it require actually? It requires n square space, order n square. Let's say I give you a straight line as a tree, then you'll require n squared space. Each node will know its parent and all its parents. So the bottommost guy will know n guys, the second bottommost guy will know n minus 1 guys, and so on. So it will be n plus n minus 1 plus n minus 2 dot dot dot, which will sum up to n square by 2 or whatever. So order n square. If you require that much memory, that's anyways too much memory. And also to calculate this much, you will also require order n square time. And n squared time in pre-calculation is a big time. Like time complexity will be n square before the query start. So your algorithm will be n square plus q times O1. Correct? That's what your algorithm will be. Like you take n squared steps before the queries come. That's how much time you take. And for each query, you answer them in O1. This part is good, but this part is very bad. Our current approach is something like this: n log n plus q log n. Here, even if you give me a big N or a big Q, it's still manageable. In your method, if N is small, then your approach is good because you got N square here, which is affordable if N is small. But here, you got a pretty fast thing. But generally, N is not that small. If N is not that small, then you want something like N log N here, and you can afford some loss here. The loss here is from O1, I went to O log N. Good. So yeah, PUI was to be calculated, right? And just remember the definition of PUI. That's the important thing. Okay, don't forget the definition of PUI. Now, what I'll do is I'll go layer by layer. So notice P question mark 0 are easy to calculate. Can everyone see this? P question mark 0 are easy to calculate for all question marks. Just in the DFS. In the DFS, I was writing this line, right? That, yeah, I can show it later, but like in the DFS, I was writing one line. That basically in the DFS, I was writing PU0 equal pref. Right? So P question mark 0 are easy to calculate. Now when we come to P question mark 1s, what is P question mark 1? Okay, example, let's say we are talking about this node. Okay, in a tree, this node is U. Now what is PU1? It's this guy, right? So PU1 is basically the second parent, which is first parent, right? So that's okay, let's say this is U, this is A, this is B. Okay, now to calculate PU1, what you need is you need to find, okay, who's my first parent, which is A, and who's his first parent. So for PU1, what all information do you need? You need PU0, right? You need this information, plus you need P of PU0. I don't know how to explain this better. I mean, this basically means, this statement basically means who's my parent. Okay, let me, yeah. So, okay, everyone was clear. How do you calculate the zeroth layer, right? Now, to calculate the first layer, the idea is you know your zeroth parent. So you know your immediate parent and he knows his immediate parent. So you can know your second immediate parent. So I'll write it more verbosely. Calculate alpha as PU0. Okay. Then calculate beta as P alpha 0. Then PU1 is equal to beta. Just try to understand these three lines slowly. Okay, no, I won't use alpha or beta also. I'll use the simple variables. X, Y, Y, Y. So X is basically my first parent, Y is his first parent, X is first parent, right? So I am U, my first parent is X, his first parent is Y. So I say, ask my parent, who's my first parent? He's X. He'll ask his first parent, who's Y, and then I'll say, okay, my second parent is Y. Okay, yeah, sorry, I made a typo here. Nice catch. Right? So everyone gets the idea of how the first layer will be. So, okay, notice I calculated the zeroth layer first for everyone. Then I calculated the first layer for everyone. Now I'll go to the second layer. So I'll do P question mark 2. Right? For P question mark 2, I'll ask, let's say I'm this U. Okay. This is X. This is Y. This is Z. This is W. Okay. Now I'll ask for PX2, what I'll ask? I'll ask for PX2, who's my, okay, now this is like 2 to the power 2th, fourth parent. I'll ask who's my second parent, which is, so, okay, sorry, U. So X, no, not X, here Y is equal to PU1, right? This guy is the second parent. And then W is equal to PY1, correct? And then PU2 is equal to W. Same idea. Second parent of second parent, correct? That's the simplest explanation. So in general, PUI is equal to 2 to the power ith parent of U, which is equal to 2 to the power I minus 1 parent of 2 to the power I minus 1 parent of U. That's a slightly complicated way of writing it, but that's the correct way. That, let's say I is 5. So 32th parent of U is basically 16th parent of 16th parent of U. This becomes 16th parent of 16th parent of U. Everyone understands this now. 32th parent of U becomes 16th parent of 16th parent of U, which can be written as, so now try to understand this one liner because a lot of people use it in their codes and it's like important to get the grasp of this one liner. It also makes your code concise. This is that one liner that I was trying to show earlier. That this is my 2 to the power I minus 1 parent. So this is this guy, PUI minus 1. And for that guy, I'm asking his I minus 1 parent. PUI minus 1 gave me the ID of that guy. And from that guy, I'm asking who's your 2 to the power I minus 1's parent? And that guy is the answer. So this thing comes here, and this thing of this thing becomes this entire thing. So is this expression clear? Take 1 or 2 good minutes and like try to think of this expression. Okay, it seems like people are getting clear of this concept and how these loops are working. Cool. The loops are working. Okay, so I said, right, p question mark zeros are easy to calculate. Then we'll move to p question marks 1. Then we'll move to p question marks 2. By question mark, I mean all the values. So the loop is actually for I goes from 1 to log n, for j goes from 1 to n. Here I'll do pji, or okay, not even, don't use j, just use u to keep it simpler and like, because everyone is familiar with the u notation now. Pui equal to this complicated expression. Just put it here. That's how the looping works. Correct, Devans. So we're only calculating this thing in the DFS because this is the base case which we need from the DFS. The tree will give this to us. Once we have this, it's easy to see that if every node knows its immediate parent, then theoretically there is enough information in this array to calculate all the remaining things. So we don't need to look at the tree again. We just need this array, and then we can build this entire thing. But building this entire thing is important for future, because later on we'll use this in the LCA function. Correct? Is the looping structure also clear to people that I'm doing this first, fixing this first, and then looping over all the nodes? Automatically it's working recursively, right? Yes, somewhat, yeah. It's kind of like a DP in some sense, that because you know the previous values correctly, so you can calculate the new value correctly also. But like the recurrence is important, that you should understand theoretically the definition of this thing is the same as this thing. So are there any doubts in the looping structure or anything? I can jump into the code because the code is not that easy for this question, like for just standard LCA. Then we can add on the path aggregate thing. The broad idea for the path aggregate thing is, I'll explain it right now only. Let's say in the LCA question itself, okay, I'll explain it with a very small example-ish idea. Yeah, let's say each node has a value also. Please tell me, how is I going up to login? Okay, I is going up to login because that's how much you can jump, right? Remember the definition, 2 to the power ith parent. You technically don't need n here. Okay, once this value reaches login, this will become 2 to the power login, which is n. So the nth parent. Now you'll never exceed this, right? You'll never, like, there is no point calculating this value for big i's. If you calculate I, say 3 login, then you're actually saying 2 to the power 3 login, which is something like n cube. But you don't have n cube nodes. You know that after login, all the values are useless because you would have climbed the entire tree up. Right? Because by the definition, it's 2 to the power ith parent. So once I becomes super big, this value is useless because there are not so many nodes in the tree. There are only order n nodes in the tree. This value is only useful to us till the time it's less than full login. Also, don't think about I that much. Always try to think about 2 to the power I here. Here also it's 2 to the power I. This is actually 2 to the power I minus 1. This is actually 2 to the power I minus 1. The reason I'm not using the power itself is because to save space. Right now I'm defining this as Pn log n in terms of memory usage. Had I used 2 to the power i's here, it would use Pn memory. That is n square memory. That's too much. That's why I'm using the exponent at those places. The exponent is just being used for memory convenience. Conceptually, you should still think of this as 2 to the power I, 2 to the power I minus 1, 2 to the power I minus 1. Conceptually. Cool. Okay. In the path aggregate questions, generally what happens is with your PUI array, right? You also have a value I array. The idea is similar. Okay. No, okay. I'll give an example question now. I'm hoping everyone is catching up with this and they don't have any doubts in the previous part. If you have any doubts, just put them there. Otherwise, we'll just like, I won't go through this again, at least from a paper pen point of view, right? We'll just jump into the implementation. Okay, I'm assuming no doubts. Yeah. So if you have values here, let's say this is 10, this is 12, this is 13, this is 5, this is 7, this is 9, this is 15. And your goal is to calculate max path query. So let's say the question is from 4 to 7, what's the maximum value? So from 4 to 7, what's the path? The path looks like, I'll color it in red. This is what the path looks like, right? What's the maximum value? There is 7, there is 9, there is 10, there is 12, there is 13, there is 5. So the maximum value is 13. Right? So let's say the question is something like this. Then the idea is, what is PUI storing? PUI was storing 2 to the power ith parent of u. Correct? We'll have a new array, value I, which will store another important thing, which will be max value. By value, I mean the values here at the side, not the node IDs. Okay, by values, I mean the values. These are the values. I shouldn't circle them. Value, value, value. Okay, these are the values, not the node IDs. These are the node IDs. We don't care about them. I mean, node IDs are used here, obviously, but value I is different. Value I denotes max value on the path from u to 2 to the power ith parent of u. This is a super important thing. Like that's the generic idea. Let me give an example. This is the first parent, this is the second parent, this is the fourth parent. Okay, this value is, let's say, 7, 3, 9. Okay, let's put this as 9, put this as 7, put this as 6, put this as 1. Then PU0, sorry, what will P50 be? P50 will be 4, correct? What will P51 be? 3. What will P52 be? 1. Now what will val50 be? It will be 1. It's like from this guy to this guy. Okay, so technically I made a small blunder here. It's actually this. Okay, max value on the path from u to 2 to the power I minus 1, 2 to the power I minus 1, minus 1 is outside, parent of it. On this path, what's the maximum value? So val50 will be this guy's own value, because from path 5 to 4, from path 5 to 5, I'm technically talking about. Now, what will val51 be? Can anyone tell me? 6, correct. Because from path 5 to 3, but I'm excluding 3. I'm only talking about the one step before. And what's the max value? So that's 6. What will val52 be? 7, correct? Because from 5 till 1, but I'm excluding 1. I'm not considering up 1 also, because it's minus 1. So this portion, and that's 7, max value is 7. Okay, so notice the way you calculated PUI, you can also calculate value I. That's the smart thing about this. So for value I, your recurrence will look something like this. Value I is equal to max of value I minus 1, comma, val PU I minus 1 I minus 1. It's very bad writing, but okay. So the idea of val array is, okay, I explained the question. You got the question, right? That sometimes you'll have a question in which you'll be given two nodes u and v, and you'll be asked what's the maximum value on the path from u to v. Similar to P array, we also have a val array, which the idea will be similar, that on paths of binary lengths. So what was the idea of P array? That every node knew some information about its first parent, second parent, fourth parent, eighth parent, 16th parent, 32th parent, so on. Val array's idea is similar. Every node will know some information about its path from itself till its first parent, path from itself till its second parent, path from itself till its fourth parent, its eighth parent, its 16th parent, so on. That's what the val array is trying to know. The max value on the path from u till its I to the power ith parent, roughly. Right? And the recurrence looks like this, which is slightly tricky to understand, but the idea is this. Let's say u is here, okay? And we are talking about the eighth parent. So there are a lot of values here, and you want to find the max value. The idea is either the max value lies here or here, either in the first four guys or in the next four guys. If it lies in the first four guys, you'll easily find it using this value I minus 1. That is the first half of the jump. And if it lies in the second half, you'll find it using this. This guy points to this node, P fourth, P, U, and like 4 steps away. And after this, you're saying from him, what's his max path here? And take the max of the two guys. So for a range of size 8, you're saying divided into two ranges of size 4 and 4. Take the max of both the ranges, and that's the max of the entire range. The first range can be represented by this. The second range can be represented by this. Are people clear why the second range is this? That's the important thing. It's written slightly, like, I mean, it comes out to be slightly ugly. No, it's not leaving any value. Val 5 computes, val 5, 2 computes. It's computing the max, right? It's not computing the sum. So val 5 2 is technically computing the max value on this part from 5 till 2. So there is 1, there is 6, there is 7, there is 3. What's the max guy? It's 7. So it computed 7. It's not leaving any value in between. Yeah, it's not leaving any value in between. It's computing from itself till it's some 2 to the power ith parent. So here it's fourth parent. So do people get this term now? That this is the second half of the jump, the max value here, and I'm taking the max over both of them. The first part, which is this thing, the second part, which is this thing. Don't think how this val array will be used right now. We'll come to that later. Just think, is my calculation of the val array correct? My style of calculating it, this recurrence thingy. And by the definition of val array, obviously, if this is how it's defined, like this is how it's defined, then is this recurrence correct? People have doubts, please put them on the discussion chat, or just say yes, that if you understand this second part of the recurrence. Can you explain the difference again? The definition. Okay. The definition was what's the max value on the path. So from 5, what was 5, val 5 0? What's the max value from 5 till 5? And the max value itself is 1. From 5 till its first parent. So from 5 till 4, max value is 6. From 5 till its fourth parent. So 5, 4, 3, 2. Fourth parent means you're jumping 4 steps. So what's the max value on this part? I'll put it in red, this part. So the max value on this part is either 3 or 7 or 6 or 1, right? And the max is actually 7. So that's why here it's 7. Okay, that is confusing. Let me know. So in the original method, what you did was you calculated parent array, right? What's your first parent? What's your second parent? What's your fourth parent? So on. Now I'm saying calculate another thing with it, which is what's my answer? What's this answer? What's this answer? Okay, let me put it in a straight tree. That way you'll understand it better. probably. Yeah. So val1 just denotes this answer. Okay. Val2 denotes this answer. Val3 denotes this answer. From here, I'm referring this guy. So his, let's say he's u, then val u1, u0 denotes the max in this range. Val u1 denotes the max in this range. In this range means this guy and this guy, whatever the maximum value you're getting. Value 2 denotes the max in 4 guys. 2 means 2 to the power 2. So 4 guys. So this guy, this guy, this guy, this guy. 4 guys. Right? Value 3 will denote the max in 8 guys, which will be something like, so 4 guys, 5th guy, 6th guy, 7th guy, 8th guy. So up till here. Devans, do you get the definition of val now? Who's the max guy in that, on that path? In this path. In this path, by I mean this node, this node, this node, this node, all these nodes. Yes, Umesh is pretty much, yeah, bang on. Like, he's quite correct. That the idea is, if you are doing a path query, this is u, this is v. Step 1 is find the LCA. This is the LCA. Step 2 is get the aggregate from u till the LCA. This part. Step 3, get the aggregate from v till the LCA and then combine these aggregates. Max guy means the node. No, I explained it earlier also. Max guy means the value. These are the values. So we are taking max on the values. I'm assuming a slightly different question now. I'm saying each node has a value associated with it also. Example in the Zor question that we were trying to do, Enoch 1. Each node has a value associated with it. And then the question becomes, from u to v, what's the maximum value that you see? So in this example, I was saying you have 4 and a 7. What's the maximum value that you see? You don't have any node 13, but still the answer is 13, because from 4 has the value 7, 2 has the value 9, 1 has the value 10, 5 has the value 12, 6 has the value 13, 7 has the value 5. On this path, the max value that you see is 13. And the val array is defined on these values. That what's the max value in this portion, or like whatever portion. Do people understand the thing that Umesh said earlier, that you're breaking, like from u to v, you're breaking the question into find the LCA first, which is this guy, and then the entire path can be broken into 2 pieces, u till LCA, one part, and then LCA to v, another part, and we combine the answers together and we'll get the final answer. Right? So now I'll jump into the implementation. I think we are done with the theory a lot, because a lot of people conceptually do understand this, but sometimes they mess up the implementation. I don't think that, like, yeah, the implementation is not considered that straightforward, to be honest. Okay, so we had this, right? And like, okay, for simplicity, let's label this u. Okay, does everyone remember this code? We had int main t test cases. The question was this. The question was, given t test cases, each test case you're given n and q, and you're then given the number of nodes in the tree and the queries, and you're given AI value associated, and n-1 lines. Basically, the tree itself is described, and then 2 nodes, and you have to find the Zor on that path. Okay. Right now we were trying to do max on paper pen, but now we lose Zor. There is not much difference. If you take any function, it won't be that different. Okay. Okay. So do people understand the DFS? Up till the DFS, at least, the adjacency list creation, the DFS is being called. The DFS is pretty straightforward. It's HU, PU. Okay. Also put value, which is just this thing, right? I'm assuming that people do understand value now. Okay, actually, let's try to find just the LCA right now. Don't care about the value. Just try to find the LCA. Okay, so right now, we'll try to do the simpler thing. That is, find the LCA. Okay. Right now, we are doing a pretty useless thing, which is just printing out the LCS. But yeah, so we have P array, and then we calculated this 2D array, parents array, which is important. And people do get this recurrence, like line 37, why it's working. Okay, can I move forward? I can't see any S's. If it's clear, then I can move, like I can start coding ahead. Cool. So on the LC array now, you first check, is my height greater than my neighbor's height? If yes, you swap them. Sorry, the reverse. So after this, for sure, HU equal HU. What's array A? Okay, array A is in this question, the Nutella path question, that each node is basically given some value. Eventually it will be useful. Right now it's not that useful. Eventually it will be useful when we are trying to solve that question. Right now we're just trying to find the LCA. Okay, now you're trying to find the LCA, right, of U and V. So I say first swap them and make sure that U is the lower guy, the deeper guy, and the difference is basically HU minus HV. Okay, now what we do is, so we first, okay, so once we have the difference, step one, kill the difference, right? So we have this difference in diff. Now we say if diff and now I'll explain this. Diff has ith bit on then. Do people get this condition? Basically, it's saying diff and 2 to the power I. Is it 0 or not? Okay, and it is non-zero only if ith bit is on in diff. That's how this condition works. It's a binary, it's a bit hack, but like, yeah, bit manipulation hack. And basically you're trying to kill the difference. Let's say the difference was 10 in heights. So you're saying difference is 8 plus 2, right? So I'm iterating over all powers of 2 from 0 to log n. And for each power of 2, basically I'm trying, is that power of, is that bit on? Okay, in 10, what's the binary representation looks like? It looks like this, right? So I first try the 0th bit, which is this guy. Then I try the first bit, then I try the second bit, then I try the third bit. Whenever I see a 1, this condition is triggered and I climb that much steps up. Is this clear that after the step, try to remember what we discussed in the notes. That we had this conjecture, right? That after killing the difference, we'll be at the same height, and there will be two cases. One case is simple case when both the guys are same. The second case is the complex case, that is both the guys are actually not the same way. So we're now at the complex case. Before this, is this portion clear? Is mainly this portion. If it's not clear, please ask in the doubts what's the exact doubt. Cool. I'm assuming it's clear. Otherwise, you can just message on the group chat that which step is not clear, or like is the def not clear, is the if condition not clear, is the I loop not clear, whatever. Yeah. Now we start with the highest power of 2, right? And we keep on going down one step at a time. Remember that we used to do 32, 16, blah, blah, blah. That's what I'm saying here. Please explain the if condition again. Okay. The if condition is basically, if say the difference is 13, how does the binary representation look like? It looks like this, right? So I'm saying in the binary representation, start from the least significant bit, and that's why I goes from 0 to log n, like in ascending order. And for each bit, see if it's on in diff or not. Diff is the height difference. If it's on, if it's switched on, then make that much size to jump. So here I'm just trying to say, in simpler words, is the ith bit of the diff on or not? The way you check that is you say, okay, 1 to the power I is actually 2 to the power I. Sorry, 1 bit shift I is actually 2 to the power I. I assume you might not know this, but this is actually bit shifting. So what this means is take 1, shift it I times. So the number of zeros that you see here is basically I zeros. So this is actually equal to 2 to the power I in binary. Right? So 1 to the power I is actually 2 to the power I. Sorry, 1 bit shifted I is actually 2 to the power I. So I'm comparing, and this is the AND operation, right? This is the ampersand. So diff and 2 to the power I. I'm just comparing the diff in its binary representation and 2 to the power I in its binary representation. Think about it. Diff looks like this, and 2 to the power 0 looks like, when I AND them together, it looks like, so it's not 0. That means 0th bit is on. Had this been 2 to the power 1, then it would look like, and the AND will look like, so the AND will be 0, right? In this case, in the first bit, because the 2 to the power 1 is this. Just look at what the 2 to the power I will be. 2 to the power I in general will be the only one of the positions will be 1, which is the ith position. Like these are I minus 1 zeros technically. Is the condition clear now? 2 to the power I in its binary representation and diff in its binary representation. We can also reverse this loop, no? Yes, you can. Yeah. But you can't reverse this loop. That's the important thing. You can reverse the previous loop, you can't reverse this loop. Now, are we doing jumping from, and we're jumping for above, right? Above, right? I don't get what you're saying, and we are doing for jumping above, right? To me, EU equal, same heights. Yeah, so this entire portion was kill the difference and make them same height. This was step 1. Now step 2 is here, which is at same height, start going from make the jump if the ancestors mismatch. Okay. So if if P of UI is not equal to P of VI, then you say we'll make the jump. That's pretty much it. I mean, the second part is literally this. Yeah. Okay, so I'll just remove these lines so that it's. Okay, now do people get the, after case 1, basically at the same height, either they are the same, so line 23 gets triggered. If they're not the same, we take the highest power of 2, we keep on decreasing 1 step, power of 2, right? Although, like, I'm just taking the exponent here. Don't start with log n because that's the size of the array, it'll overflow. Right? Log nth access element is not accessible, log n minus 1 is accessible. And then for each guy, you just say PUI equals, like, if they mismatch, if the ith parent of u and 2 to the power ith parent of u, right, and we claim, and eventually conjecture here, what was the conjecture? That 1 step away from the LCA, right? That was the conjecture. So to get to the LCA, I calculate x, which is basically the LCA, which is just one parent of U. That's it. Do people get this now? The second part, basically, I'm doing in decreasing powers of 2. For each guy, I'm saying if the parents mismatch at that level, like the 2 to the power ith parents mismatch, then I climb that much up. So remember from the samples that we were talking about, say the height difference was 20. Then when you try I equal 5, so you have 2 to the power 5, 32. So 32th parents will match. Then 16th parents won't match. So this condition will actually be triggered for 16th. Then 8th parents will match. Okay, how are we knowing that changing U and V will not exceed LCA? Good question. So after this point, when the heights are same, LCA of U comma V is equal to LCA of PU0 comma PV0. Think about this. So, and you can keep on doing this. LCA of PU, F of U comma 2, F of V comma 2. The LCAs will remain the same. If both of them are climbing at the same speed, if both of them are climbing 5 steps up together, then the LCA will still remain the same. Obviously, once you hit the LCA, like you can't keep on defining this, but like till the time you haven't hit the LCA, this value keeps on being the same. Here, LCA of U comma V just means, yeah, because the heights are same. Had the heights not been same, you can't say this. This is important. Like heights being same is very important to be able to say a statement like this. Okay, here you might have forgotten. F of U H meant Hth parent of U. That's what we defined it in the notes. Right? So everyone gets this? Why is this thing working? Good. So, okay, do we want to try this first? Like just like compile this code and like actually see that it's working or not. Also, let's make this portion simpler. Just say here return this. One question 5 2 1 2 3 4 5. Okay, then one has a child 2, one has a child 3, 2 has child 4, 2 has a child 5, 3 has a child 5. Okay, I did something bad, I think. So N and Q come, then N elements, then this UV. Okay, so the tree was this much. Yeah, so one had 2 children, 2 and 3, right? And 2 had 2 children, 4 and 5. So what's the LC of 3 and 5? Think about it. The LC of 3 and 5 is actually 1, which we did print out correctly. Right now, we are not actually tackling the original question, which is asking the XOR value of the path. We are just saying, what's the LC of 3, 5? So notice 3, 5 LCS is 5. I can take another example in this question only. What's the LC of 3, 5? It's 1. Okay. What's the LC of 4, 5? 4 and 5 are just like the LCS 2. So I'll just put these two guys and it comes out to be 2. Cool. So everyone can see it's working, right? I mean, obviously these are not strong enough test cases to be able to see, but yeah. I mean, I'm confident that it's working. I think it should be. Yeah. Okay. Now we calculate the val array also. Okay. I'll add the val array and just show you how it will work. So first, how will the base case look like? Val U0 will be A0. AU. Val, what does val denote? Okay, remember that. The aggregate on that path. Correct? The aggregate on that path. Now, so val U0 will denote A0. What will the remaining DFS will look exactly the same. Now here, we were calculating this value, right? We'll also calculate value I, which is max. Okay, in that question, I was doing max. Here we'll do XOR because the question is asking us for XOR. So XOR is this thing. Correct? Also make sure that this is an important thing. P0i is equal to 0 and val 0i is equal to 0 also. These are basically, notice once you jump a lot of up, like basically let's say n in question is only 100, but your I is let's say 10, then technically you're referring to 2 to the power 10, which is 1024th parent, which is not defined. But our implementation still works. Why? Because notice I do a very hacky thing here, which is I say parent of 0 is 0 itself. So basically it's a self loop at the top of the tree. So the top of the tree is 1, parent of 1 is 0, and then parent of 0 is 0 itself. So it keeps on looping over there. So basically 1024th parent of 0 is also 0 by definition, right? So you don't have to care about that nitty-gritty detail, that can you go to capital log n or not, because even though capital log n, yes, 2 to the power 0, yeah, like, yeah, Umesh, you're correct. Val of this guy is itself the value itself. And also, yeah, val of 0 is 0. Okay, it can't be 5 or anything, because I want to keep here the identity function for XOR. This is important to get the idea of, because notice I might sometimes unnecessarily XOR this thing with val 0. I'll give an example. Let's say n is small, I is big. Okay, you're calculating value I. If the value I entire portion is actually inside value I minus 1, because you've already hit the fucking ceiling. Like I is already 10, so value 9 already actually consists of the entire thing, because 2 to the power 9 is still 512, which is bigger than 100, but you're still XORing it with something. So this thing should be identity. That is, after XORing with this thing, it shouldn't affect your answer. Mehul, we are discussing Enoch 1. So that's why this is identity. I won't explain this much in detail. When I see XOR, I think it involves some XOR property. Because there is an alternate solution which involves XOR properties. I'm doing the more complex solution to just show you the path aggregate idea. I mean, here I'm doing the XOR operation, but you could replace it with the max operation for all you know, if you wanted to do that. Exactly, Umesh, you're correct. Yeah, you got the idea, right? Yeah, that if you're doing for max and negative values can be there, then 0 is incorrect. Then you would need int min identity function for basically something like an identity function for max. Yeah, because basically once that's applied, we want it to be like have no effect, because technically there is no node 0. We are just fictitiously creating it. There actually doesn't exist a node 0 in the tree. We're just using it for convenience so that we can still use this capital login and not try to find the actual login. Had you used a different implementation idea, then you would see n is 100. So your small login will actually be 6 or something. Basically, you'll actually calculate what's the highest power of 2 I can go to and only calculate values up to that point and not calculate unnecessary values. That's another implementation idea that you can use. I mean, that's the alternate implementation. Okay. Now our LCA function will start returning a pair. So earlier it was just returning the LCA. Now it will return a pair. And what will be the values of the pair? It will return LCA value, like, sorry, LCA of u comma v and XOR on the path from u to v, the entire path. So it will just have the fucking answer in the second attribute. It'll have the entire answer. So you'll just print out the second value and you're done. Okay, like that's what we want. Okay, so we have the val array. Now I'll delete these lines, or okay, maybe I won't delete these actually. You do the okay. Now you'll have this int arms equals 0. Okay, and eventually you want to return something like this, something like this. So how in the step 1, when you're killing the difference, you'll also try to update the answer. Right, the answer will also keep on climbing up as you're climbing up PUI. Like the answer will basically, the answer will say add this contribution to my path. Till the time the height becomes equal, keep on adding these contributions. And also when you reach, if you reach the height itself, then you can just return the answer. You're done. Let's think. Had u and v been same, this difference would be 0. You'll come here, you'll come here, you'll come here, you'll come here. You won't return the correct thing, notice. So you need to actually do XOR it with the last thing. Right? Okay. Answer do people get this? Answer up till here does not include the last value. Had you printed just the answer, it would be wrong. You actually need to XOR it with AU itself also. Yes, no, anything? If you don't get it also, please speak up or put it in the chat. Yeah, the reasoning was that you have this answer, right? And you'll XOR it with some things, but notice that we had this -1 in our definition of the answer. And so you'll actually exclude the last value by mistake. Example, assume u and v come out to be the same in the LCA question. Let's say u and v are actually the same. Then this thing won't trigger. The difference will be 0. Because the difference is 0, this if condition will never be triggered. And you'll come here at line 27. And your answer will be 0. It hasn't run this line ever. So you're technically giving the wrong statement out. You actually need to XOR it with AU. Because your answer is not 0. A single length path also consists of itself. Right? And then, okay, here, when you are jumping, only then you should update your answer. So when you jump, what will you do? You'll do answer equal to answer XOR val ui XOR val vi. Right? But whatever answer we have on the paths, just aggregate them with the new jumping path answers that you're getting, which is value and val vi. And eventually, we'll again answer XOR is so I'll write this like this so that it's clear. Right? And notice that we will be one step away. So because we are one step away, LCA has not been included in ANS till now. Can you believe when working? Okay. So you remember what's the definition of val array, right? And if you remember the definition of val array, which is basically val array is val ui is equal to XOR of the path from node u to its 2 to the power I minus 1 parent. Right? That's the definition of value I. Now, once you have the definition of value I, you can see this construction, line 74, that I'm just taking XOR the first half of the path with the second half of the path. And once you have XORed the two paths, this is the first path is easy, right? This is the value I minus 1. This is the first path, first half of the path, and this is the node that is the starting point of the second part, second half, and then the entire thing is the second half. Once you XOR both of them, you have this value I array. Now I change my LCA function to say it will return a pair, and the second value of the pair will be the answer itself. So it will return LCA of u comma v and the XOR of the entire path from u to v. That's the answer itself. To get the answer, I'm saying have this answer variable, and whenever you make a jump using p array, update the answer also that time. Basically, whenever you make a jump using PRA, what you're doing is you're consuming some part of the path. So when you're consuming some part of the path, also consume its XOR value in your answer array, in your answer variable. So when I jump here on line 23, I also consume this part, because when I'm jumping up till this position, I'm kind of like forgetting about these nodes that I'm jumping over. So to account them in my answer, I'm XORing them also, right? And then here also, when I'm jumping over use some ancestry, like to some parent of it, and v's parent of parent of v's, then technically I'm removing some portions of the path. Think about it this way: from u to v there is a path, and I'm shortening the path step by step till the time I hit LCA from both the ends. So when I'm shortening the path from both the ends, whenever I shorten the path, the path that I removed has to be consumed also by the XOR variable, by the answer variable. So that's why I'm XORing it again and again with the correct values, which you can see here. Just the vals, the val array is the idea. Clear now? Yeah, thinking about this way is, I think, actually simpler. That u to v there is actually a path, and you're making the path shorter and shorter by making u and v come up in the tree. And whenever you come up in the tree, you are killing some portion of the path, and the portion you're killing has to be consumed by your XOR variable. So that's pretty much the implementation. Yeah. Okay, we got 4 and 2. Interesting. I think I got mismatched on the answers. I'll try to figure out what the bug is, if there is any. Okay, 3 to 3, I got the correct answer. 3 to 4, will I get the correct answer? Let's see how the tree looks. Okay, 3 to 1, I got 1. Is that correct? No, I should get 2, I think. Wait. Okay, so I have some bug, I think. Now let's say the queries from 3 to 1. I get 2, but actually the XOR should be 1 XOR 3, which should be 2. Oh, okay. So I got the correct thing. Sorry, my bad. So I'm getting the correct thing for 3 to 1, and for 3 to 5, I'm getting the incorrect thing. So 3 to 1, I'm getting the correct part. Then 3 to 2, what am I getting? Am I getting 0? No, I'm not getting 0. Okay, so there is some bug. Nice. So let's try to debug this. Okay, you can see how I try to debug this. I mean, sometimes it gives useful ideas. I'll just print a lot of statements first, just to see which variables are actually mismatching probably. And I see this. Okay, I think I know what the issue can be. After the step, and then okay, so 3 and 2, u was 3, v was 2, answer was 0. Okay, pretty much every time the answer came out to be 0. Wow. So we never actually made any jumps. That's the issue, right? Yeah, because 3 and 2 are just one step away from the LCA. So we never actually made any jumps, and then that's why the answer never took those values into account. Okay, I understood the error. The error was here, I think. Yeah, in the jumping portion eventually. It should have been this. Okay, and here also, I'm not sure what this thing should be. Should it be value 0 or should it be? I think it personally doesn't matter. I think it should be a u only. Yeah. I'm not entirely sure whether fix the bug or not, so I don't want to explain right now. My thought process. Okay, 3-2 comes out to be correct. Now try 3-5 comes out to 5. Okay, I think I've got the bug correctly, but like I'm not entirely sure. But like the idea was that when you're here at the answer at the stage, it will not have the topmost guys and the LCA. It won't have all these three things. So I added all these three things manually because the topmost guy won't be there, because when you're jumping, the definition was that, yeah, the val array actually doesn't keep that guy inside it. So you actually need to put him. And you also need to put the LCA in. Right. But here you just need to put the value in because let's say, okay, how's the case? U is at the bottom, V is at the top, right? U is at the bottom, V is at the top. You'll climb some steps up. You'll come up till one step. You'll run one step short. Yeah. So you'll climb, you will climb, and hit this position, but he won't have this value itself. So he'll add himself. Yeah. I think this is correct. Okay. I'm 100% sure this implementation is correct because of the last portion, but like, okay. Have we submitted the correct thing? Let's go see that. Is it the correct code that we submitted, or we did be submitting something incorrect? I think we submitted the correct thing, right? Yeah, we submitted the correct thing. Okay, TL lead. One issue can be fast IO because we didn't use fast IO. Printf scanf, yeah, I'm thinking of that sort only. The issues there only. I mean, I don't think we are doing anything super slow in our approach.
let's just see this again. T is being taken, then U and V are being taken. Oh, sorry. This was a lame bug. I'm not clearing the adjacency lists. Yeah, I didn't check whether I'm clearing all the data structures or not. So I should clear the adjacency lists. Yep. And what else? What else global arrays we have? We have P, H, val. These will all be overwritten correctly next time. Yeah. But like clearing the adjacency list was important, which we didn't do. Yeah, even that will cause a TLE because your adjacency list will be filled again and again and again and again. Eventually you'll like you'll be iterating on like two big lists, very big lists. And even it won't be a tree, so it will be infinite recursion. Yeah. Okay. So yeah, keep in mind, I will somewhat also mention this, that I was not using visited array. The loss was because I was not using visited array. If I don't do this, think about what was happening. I was putting in more and more stuff in the adjacency list as more and more cases went by, right? And because more and more cases went by, I was putting more stuff in the adjacency list. And the thing was not a tree. Like say, it's kind of like saying I combined in the second test case, I would be combining the adjacency list of the first and the second, of the first case and the second case. So you're combining two trees, superimposing one on each other. So it won't be a tree anymore, right? It can be a graph, generic graph. And because of that, my DFS will run into infinite recursion. Because my DFS assumes that I can only have one guy as my parent. So I only need to avoid him. But if there is a cycle, say there is a triangle, if there is a triangle in the graph, then this DFS is infinite loop on that triangle. I can keep on going through that triangle again and again and again, because you will see, like, let's say prev goes to u, goes to v, goes to prev. Now u will not go to prev, but he'll go to v. V will not go to u, but he'll go to prev, and it'll keep on happening. So probably the TLE came because the DFS was going into infinite loop. Yeah. Anyways, so this technique works, right? So this is the LCA thing. It's quite long, I feel. I mean, is there any general consensus of whether people want to have the second thing also or not right now? Or are people tired? If people are tired, we can probably have another graph session sometime later for the second topic, which is like BFS or extra. Surinder, as a software engineering point of view, there is not much benefit. As a generic coding practice, people don't recommend to do this. But in comparative, it's preferred because, so the solution had nothing to do with that. Concept correct if you are using this technique. There is an alternate approach to this question, which is much simpler. And I would recommend you to try that out. The approach is something like this. I can give the actually the int zor from root n. Okay. And in the DFS, okay, I won't remove this code. Let's see what can I do. Okay. I'll just copy this file. Yeah. So your question was, yeah, it's passing around less parameters. Also, when you're passing around parameters, you have to make sure that you're doing pass by reference and not pass by value. Sometimes people make this mistake that they by mistake do pass by values. When they do pass by values in a lot of functions, the time complexity becomes a huge pain, because let's say you're passing a vector and the vector has n elements. And if you're passing it by value, then you're technically doing an entire copy constructor on the vector. It takes a lot of time. In global, you know that you're not passing things, so you don't have to keep that mental overhead that am I passing things or not. Okay, I'll show the simpler solution to this question, which is like super short, and it exploits DFS property. Sorry, ZOR property. Okay. So you have this, right? You cleared the adjacency lists. Then you had NQ, UV. You took the adjacency list. You do a DFS. In the DFS, you have this additional parameter now. What's the XOR up till now? So XOR from root till now. Just make this super big, long variable, right? So XOR from root till U is basically this value. And then whenever I'm going inside the DFS, I take this value and I XOR it with the new node that I'm going to, correct? So basically this value stores, like this stores XOR from root U is equal to XOR of the path from U to root. Right? Everyone gets the how this value is calculated and why it's calculated correctly. Now the answer is pretty simple. The answer is just the answer is almost this, but not exactly this. So okay, and notice what will this answer variable look like? The XOR has this property that x XOR x is 0 for all x in integers. Right? This property is there. So when you have, let's say, a path from U to V, which can be broken as paths from U to root and root to V. Okay. Now XOR of path from U to root when XORed with XOR of path from root to V, a lot of stuff cancels out and it becomes XOR of path from U to LCA, XOR of path from LCA to V. Sorry, technically LCA minus 1 and V to LCA minus 1. Do you get this idea? That basically everything above the LCA, they cancel out with themselves. Let's say the LCA is node 7 and above it, there are 5 nodes till the root. Then all those guys just cancel out their XOR values, including the LCA. The LCA also cancels out its XOR value. So that's why you need to eventually XOR again with the LCA because the LCA is not included. So if you just do this much, then your answer will be this. If you just do the first 2 XORs, your answer will be just this much. XOR of path from U to LCA minus 1, XOR with XOR of path from V to LCA minus 1, but you won't have the LCA itself. So you need the LCA also. So you say in the last statement, answer is equal to answer XOR A of LCA of U comma V. Obviously, I deleted the LCA array and everything, but if you have the LCA function with P recomp, then just use it. Right, this won't work right now, but like that's the idea. Okay, previous approach Akash was much more general. We didn't exploit this property that things cancel out. So in XOR, there is this property, right, that x XOR x is 0, and that's why the paths just cancel out above the LCA. So this question is slightly easier. I mean, if the question was take the max on the path or min on the path or GCD on the path, something of that sort, then you don't have this property that answer from U to root combined with the answer from V to root will give you something useful. In this case, it was giving you something useful. Notice answer from U to root, which is this thing, and combined with the answer from V to root actually gave you a very meaningful value. But for mins, maxes, this value is pretty useless because it will have the, like, had this question be on max, then this value would be used. And like, let's say you had this max and you did a max on both these values, then you can realize that this value is useless because it might be the case that the root itself is super big. Like, let's say A of root is, I don't know, plus infinity. Then answer will become plus infinity and it won't be meaningful. You don't have any information. You can't cancel stuff out from max. if had it been an addition or subtraction question, you could still do that. But because it's a max question, you can't cancel stuff out. So the previous approach was much more generic, where we only consumed information on the path. We didn't consume any extra information. So we didn't need any property like this of cancellation, because we were not consuming any extra stuff. Even max will work because we are not going above the LCA anyways. From LCA to root, that path is untouched in the previous approach. In this approach, the problem setter exploits this property that the path from root to LCA will actually come twice, and XOR cancels when things are XORed twice. He's using that property. That's why the solution is much simpler. Just knowing how to get the LCA works. You don't need to know how to do path aggregates on LCAs. Yes, if you're trying to calculate max with the whole path has in from that node till root, then this is useful. Yes, then you can have max from root or max from root, whatever, max from root array. But if you're not going till, if you don't want to go till root, then it's useless, because then this information is kind of giving you something that you don't want. You can't cancel stuff out from max. If you have max of a path, of a big path, you can't subtract a small path from it. But in XOR, you can do that. In XOR, just XOR that small path again. If you have the XOR of a big path, just XOR that small path again, and that will cancel it out. In addition also, you can just subtract that path. Is it possible to do such question using something different other than generic approach in such problems, as generic one might be lengthy? I mean, this one was the slightly special approach one, in which we just calculate the LCA. Okay, in this question, I know that you have to calculate the LCA no matter what. I don't think there would be any solution which doesn't even calculate the LCA. To calculate the LCA, the one approach is binary climbing, which I showed you guys. So LCA can be calculated by binary climbing. Also, it can be calculated by segment tree on Euler tour. I'm not sure if you know this. So Euler tour is basically a technique on how do you represent a tree as an array, and then you run a segment tree on it. It's slightly complicated. I can maybe share some links. Then there is a square root and technique also. What do you mean by generic approach? The previous one, is it? I don't get what do you mean by generic, the word generic. If you meant the previous approach, then yes, that approach is much more applicable. Like that approach will work on every question of path aggregate. Yeah, the previous approach will work on like almost all path aggregate questions, whereas this approach was specific to XOR. Like only in XOR we can exploit this max from root XOR from root property. But like had the function been slightly different, or yeah, something else was asked, then obviously the previous approaches, it can be lengthy slightly, I agree, but it's like it's a superset power tool, some sense that it can solve more questions than this thing. Yeah, and it might be slightly slower also by a log n factor or something. Like yeah, like slightly slower. It's possible that it's slightly slower. Like maybe this method might get you over somewhere, like if had you not been able to not have to calculate the LCA, because if you make error in cases, it would become a headache. Agreed, it just does become a headache. I mean, that's why you do printing and stuff. But anyways, you have to find the LCA in most of these questions. So if you're writing the LCA code itself, then adding the path aggregate is just like 5-7 lines. Like adding the val array everywhere at correct places is just like 10-line change or something. So if you can write the LCA function itself correctly, then making it path aggregate is relatively simpler, I would say. Writing the LCA function correct itself for the fast log n one is challenging, but I think it's required. Like, okay, binary climbing is probably the simplest method, to be honest. Sure. So if you know what Euler tour is, which is basically a array representation of a tree, then what you do is, if LCA of u to v becomes okay, so in the array representation, what you do is, for each element of the array, can you please explain line 34? Okay, I mean, you can't subtract. Okay, by the word subtract here, I mean a very particular thing. Okay, example, let me give you. Let's say path 1, 2, 3, 4, 5 has max equal 30, and path 3, 4, sorry, okay, and let's say path 3, 3, 2, 1, max equal 20. No, max equal again 30. Now, can you say what is the max of the path 5, 4, 3? You can't write. Even though you have these two variables, you know the max of the big path and you know the max of the small path, but you still can't say what's the max of the subtracted path. Whereas in XOR, you could say that. You could cancel out stuff. If this is the XOR and this is the XOR, you could just say XOR basically take the bigger XOR and XOR it with the smaller XOR. So it becomes 0. So you know that the smaller path has a XOR of 0. But you can't do that with max, min, GCD. You can do it with sums and XORs, mainly addition, subtraction, and XOR. That's the thing that cancels out. Basically, the function needs to have an inverse. That something for every x, there should be a y, such that x operation y becomes identity. Notice in addition subtraction, you also have a y. If your x is 5, then y is minus 5. And your identity is 0. In XOR, if x is 0, 5, y is also 5. And identity is 0. But you don't have this in max and min. If x is 5, no matter what you do, you can't reach identity. Maybe if x is minus 3, you can say that y can be 0. But for x is 5, there is no y. No matter what y you put, your max of x comma y will come out to be greater or equal 5, which is not equal to identity. So yeah, so in the LCA, u comma v basically becomes max height of a node in the subarray from u to v. By subarray from u to v, I mean in the subarray starting at node u and ending at node v. Yeah, that's what the LCA becomes. So because it's max height in a subarray, this becomes a range min query on a subarray in a segment tree. I mean, I can't explain Euler tour itself, but like the subarray thing basically comes from the Euler tour. That's why you use segment tree on Euler tour. Yeah, even segment tree or sparse table or whatever. So segment tree on Euler tour is still order log n. If you're interested, you can read up on sparse tables on and sparse table. And if you use sparse table on Euler tool, which is kind of like a segment tree, but slightly weaker, that you can't do updates. But okay, so sparse table versus segment tree. For those who know it, the difference is sparse table can't do updates. Only one-time construction is allowed, but faster query, O1 query. Segment tree can do updates in login. Okay, I mean, you can do updates on sparse table also, but it'll take order n, so it's pretty useless. And slower query, O login. So if you use sparse table on Euler 2, then you can find LCA in O1, which is pretty good. Like you can actually find LCA in O1 also if you want to. But people generally don't prefer to write this because it's so tedious and so long, and because login generally doesn't make a lot of loss. So binary climbing is, I think, generally more preferred. Yeah. Okay. I don't think people would prefer to do that, like the second topic today, because this went on for very long and it's quite tiring, I feel. Akash, I don't think so. And like, I think we'll end this session right now, or like in 5 minutes. And yeah, I think maybe we can have the second part of the session next week or something, like on some weekday. But yeah. You're welcome. Okay, and you guys can fill the feedback form also.